Hey, good morning, ladies and gentlemen. So I see a lot of people have had fun on the banquet and are not here this morning. We have a much smaller audience than yesterday. I hope everyone had a great time on the cruise. How was that, ladies and gentlemen? Good? All right, thumbs up. All right, I see a lot of smiling faces. Well, behind masks, of course. Today we have an exciting program for the last day of the conference, of the main conference. Then tomorrow we'll have workshops. But today we're going to be starting with more short talks. We also have a Test of Time award and panel. That Test of Time award goes to a paper that has been over 10 years old at the RSS conference, and it goes to Emilio Frizzoli and Sertac Karaman for their paper Incremental Sampling-Based Algorithms for Optimal Motion Planning, and we'll see a talk by Sertac Karaman and a panel to discuss this paper and its significance in the history of this work. We'll also have the award ceremony in the afternoon, followed by the RSS Town Hall. And so the Town Hall is actually a very exciting part of RSS. It distinguishes RSS from many other conferences. And here we talk about the direction that our field is going in, how the conference can best serve our community, and what kind of suggestions you have for us to make this a successful event and also help shape the future of robotics. In terms of, let's see, do we have this clicker? Can we advance the slide? You can just advance the slide. Okay, just as food for thought, as possible questions for, open questions for discussion during the town hall. Of course, any comments about the paper review process or the conference program are very welcome. We also have lots of questions that we ought to be thinking about in robotics today. So for example, we have found that demands on people's time have increased over the last couple of years, and it seems like reviewing is becoming less of a priority for many people. And so we want to think about how we can ensure high quality reviewing as demands on our time grow. So also, I have an open letter to the community about systems research. We call this the Robotics, Science, and Systems Conference, but you will be excused if you ask the question, where are the systems papers? We don't have all that many. So how do we ensure that systems are an important part of the work that we do in the robotics field, and how do we try to cultivate that in our conference? If you came into this conference and you thought that you had stumbled into Coral by accident, you would be forgiven, given that about 2/3 of our papers are learning related. So this is, of course, a very highly subscribed field, some would say oversubscribed topic in our field today. How do we deal with the vast number of papers in this area? How do we get good signal rather than noise? And also, how do we make sure that the field is going in the right direction? We have many underrepresented areas. I will talk about these more at the start of the town hall, giving you more statistics about these different areas, but any kind of mechanical engineering work, medical work, systems work is very underrepresented at RSS. What do we do about these areas? There are things outside of our robotics community that are happening in the world, and many of you might be thinking, oh gosh, what am I going to, like, the next 10, 20 years are going to be a disaster. What is robotics? What's the role of robotics in all of this? And this is something that maybe it's a bit off topic, but I don't think it is. I think we ought to be thinking about broader social trends and how robotics can fit into that. So without kind of giving you any kind of direction on this, just mull these things over, and we can talk about them during the town hall. If we could skip to the next slide. All right, so our first paper session is chaired by Elaine Short. I'll turn it over to her. You can clap.
Yes, you can clap. Clap for me. All right, so to start us off, we have 3 virtual talks, and our first talk is on Kernel GPA, a deformable SLAM backend, being presented by Feng Bai.
Hi everyone, it's a great pleasure to meet all of you guys here, and also it's a great pleasure to attend this year's Robotics Science and Systems Conference. My name is Fusebot. Today I present Kernel GPA, a deformable SLAM backend. Here is a typical SLAM problem. Here we have odometry and landmark measurements. Now imagine we don't have odometry. Is the resulting problem solvable? Without odometry, this problem is called generalized request disanalysis, or GPA. In particular, landmark-based SLAM without odometry is called rigid GPA. From rigid GPA, we can solve both poses and landmarks. Having said that rigid GPA is sufficient to determine poses and landmarks, what if the environment is deforming, where each point cloud has different shapes due to the existence of deformations? To accommodate deformations, we must use more general transformation models in GPA, for example, the affine transformation. An even more general form is the linear basis warp, or LBW. In general, a LBW contains a affine part and a nonlinear part, and all the parameters are linear and constraint-free. The nonlinear part of the LBW admits a dual formulation, thus we can obtain a kernel-based transformation model. The kernel-based model is more flexible than LBWS and avoids the complication of choosing nonlinear basis functions. For deformable transformations, we need to design transformation constraints, otherwise the solution will be trivially zero. To proceed, we introduce a concept called shape covariance matrix. In specific, the shape covariance matrix is only related to the rotation, and on the rigid transformations, the eigenvalues of the shape covariance matrix are preserved. Here are the transformation constraints we use, where lambda contains the unknown eigenvalues of the shape covariance matrix. The first constraint fixes the translation and restricts the shape covariance matrix to MM transpose. The second constraint fixes rotation because it forces the shape covariance matrix to be of the diagonal form. We also use regularizations to control the extent of allowed deformations. By putting things together, we have the overall formulation for GPA with deformable transformations. This problem can be solved globally up to unknown lambda, and we can design the lambda afterwards with additional assumptions. To solve this problem, we first reduce the above to an optimization problem of M only. And then applying variable replacement, we see the reduced problem is a spatial eigenvalue problem. This eigenvalue problem has a closed-form solution if the O1 vector is an eigenvector of Q, which is true for LBWS and kernel-based models, as we can prove Q times 1 equals to 0. Following the discussion in our RJCV, this is due to the existence of a free translation in the transformation model. Now we have solved the problem up to an unknown lambda. The next step is to design the lambda with additional assumptions. Here we assume the transformation to be as rigid as possible. We use pairwise prerequisites in RJCV by assuming some points are globally visible in all point clouds. This is a strong assumption for SLAM, as observations in SLAM are typically local. Instead, in this RSS, we propose to solve a unified optimization, which is a standard nonlinear least squares that can be solved by Gauss-Newton iterations. We give a robust and cheap initialization to this problem. On the left is the initialization process. We first eliminate translations and calculate a fine relaxation to the rotations. Then we use the orthogonality constraints afterwards to obtain a linear least squares in lambda. This gives a closed-form initialization to lambda. We use Gaussian kernel for experiments and design the kernel bandwidth and regularization strength by cross-validations. We show the error statistics of different transformation models, Euclidean, affine, TPS, and kernel GPA. In particular, kernel GPA gives the best performance. We compare the new lambda estimation method with the one in RJCV. For a dataset with a lot of missing correspondences, the proposed new lambda estimation method is better. We check the poses solved from the unified optimization. These pose estimates are basically the same as the ones obtained from rigid GPA. Lastly, we propose TopX, a city point cloud dataset with correspondences. The correspondences are partitioned into several categories. We use one category to estimate the transformation and the others to validate the performance. Consistently, kernel GPA gives the best results. On the right, we provide some qualitative examples. That's all. Thank you for listening to the talk, and see you next time. Goodbye.
Hello, everyone.
Okay, our next talk is Curl, Continuous Ultra Compact Representation for LiDAR, presented by Kai-Cheng Zhang.
Use a pipeline that can compress and enhance the density of the LiDAR point cloud at the same time. A traditional 64-channel LiDAR generates about 1 terabyte of data per day, so for autonomous driving, having all data recorded is hard. What's more, when the robot working in the indoor scenario, we would expect the 3D map could be as precise as possible to satisfy all different tasks. Even a bedroom point cloud map like this, size could reach about 4.2 gigabytes, which could be hard for mobile robots to load in real-time applications, and it consumes lots of RAM memory for infrequent usage. Most LiDAR point cloud contains lots of holes, therefore, how to enhance the density and reconstructing the surface from the existing sparse point cloud is also a problem. For point cloud compression, recent works depend on the tree structure, which is hard to represent on known regions and enhance density. There are some works that can do upsampling, but none of them can do compression at the same time. So how to achieve both abilities? Therefore, we introduce spherical harmonics functions which are orthonormal and complete, which means all 3D polar functions can be decomposed into a series combination of spherical harmonics functions. This is similar to Fourier series regression, but LiDAR point clouds usually contain some sparse regions. By using the same degree for encoding, we can see from reconstruction that higher density could provide better prediction results. The LiDAR point clouds usually contain a large number of points, so computation costs could be huge by applying spherical harmonics functions directly to it. So we designed the Curl pipeline to solve these problems, which mainly contain 3 parts: meshing, upsampling, and encoding. To solve the sparse problem, we proposed a meshing method for upsampling. We first project points onto a 2D plane, then apply the knowledge triangulation. Finally, we can get a watertight mesh by projecting back connectivities. The next steps are upsampling and denoising. After upsampling from mesh directly, there are lots of spurious points. To remove these points, we use the depth image of the original point cloud to generate 2 kinds of binary masks. The first one is the point grid, representing the occupancy pixel of the depth image. The second masks are for cliff detection, removing wrong sampled points between sharp gaps in 3 different directions. We first increase the resolution of the point grid to match upsampled point cloud. Then we project this back to cliff detection masks to correct the point grid mask. Finally, we apply this mask to the noisy point cloud to clean. The next step is extracting spherical harmonics coefficients. To reduce computation costs, we divide the entire upsampled depth image into many patches. But how to get suitable degree? For existing points, a higher degree can provide better reconstruction results. However, overfit could occur if the degree is too high for unknown regions. So we select diagonal pixels as testing cells, and the rest of them are training cells. To cover the gaps between neighbor patches, we extend the training cells. Then we iteratively increase the degree to find the lowest error for both training and testing cells. With coefficients and masks, we can do a continuous reconstruction now. Here is the result of meshing upsampling. We have fewer errors compared with the LiDAR super resolution method. This is one scan of a 64-channel LiDAR point cloud in the university. The ratio of 1-to-1 reconstruction error is at the level of millimeters, which is lower than the error level of the LiDAR sensor itself. For continuous reconstruction, Curl can produce more than 10 times of points than before and only takes 11.9% storage space of the original. The green map is after integrating the denser point clouds. Our result takes less storage space but with comparable points number with the ground truth. Here is another map example in the indoor scenario. We can increase the point number to about 30 times more than before, and the size is only about 18% of its original. In summary, we have 2 main contributions. One is the 3D LiDAR point cloud representation pipeline. The second contribution is an efficient meshing method and upsampling technique to solve the sparsity problem. For more information, please find our paper and code. Thanks for watching.
Our next paper is SEER, Unsupervised and Sample-Efficient Environment Specialization of Image Descriptions, being presented by Stefan Schubert.
Hello, my name is Per Neubert, and together with Stefan Schubert, I work on specializing descriptors for a particular environment in the context of visual place recognition. I will first shortly introduce the underlying problem and idea, and then present SEER, our algorithmic approach. The basic task is to associate a query image like the one on the left from the Karl Marx monument in Chemnitz with a set of images of known places in a database. An important tool are general place recognition descriptors, like netflat or HDZ-delf, that indicate the similarity between images of places. I call them general because they work for a broad range of environments. For example, the typically used netflat model was trained on urban images from the city of Pittsburgh, but in a way that it can be applied to images of other cities as well, like Chemnitz. However, this netflat model does not work well for an open natural environment, like in the Norland dataset. But we can assume that netflat trained on natural images, more similar to Norland, would create a better place recognition model for this environment. And thinking even further in this direction, what if we train netflat directly on the Norland database images? Or more generally, what if we train any descriptor directly on the database images? The hope is that the descriptor is then optimized for this particular environment. An important observation is that in place recognition we always have a database that we can use for training or fine-tuning. However, there are some challenges that might prevent a straightforward training of a descriptor like netflat. The database might be small, for example just a few hundred images. Very importantly, we do not have labels. There is no ground truth information about which database images show the same place. And finally, in downstream tasks like loop closure detection for online SLAM, we might not have a lot of time or computing resources for training. And of course, this descriptor will be environment specific and not be applicable to other environments anymore. This leads to the following problem statement of this work. Is it possible to adapt, improve, or fine-tune general place recognition descriptors for a particular environment, for example the city of Oxford, in a completely unsupervised fashion and with low sample and runtime complexity? We propose a simple unsupervised greedy learning algorithm to approach this problem. SEER stands for Sparse Exemplar Ensemble Representations. The first step is a simple greedy learning on the database in order to create an internal representation or model M. The input are general place recognition descriptors like netflat or HDZ-delf. SEER starts with an empty set M and adds for the first incoming database descriptor an ensemble of k sparse exemplars. An exemplar is simply a sparsified version of the input descriptor, using a weighted sampling to select about 5% of the input dimensions with a large absolute value. For each further descriptor, we test whether there are already k-similar exemplars in M that can be reused and newly create the missing number of exemplars as before. The purpose of the second step is to apply the exemplar ensembles to database and also to query descriptors in order to produce the SEER output descriptors. Each incoming descriptor is compared to each exemplar, and the resulting environment-specific descriptor is simply the sparse vector of similarities to the most similar exemplars. The output descriptors can then be used for image retrieval and place recognition in the same way as general place recognition descriptors. We implemented and extensively evaluated the simple algorithm. There are 6 main insights from the experimental evaluation. The place recognition performance improves over the raw general descriptors. We evaluated this on 23 sequence comparisons from 6 environments. We can see that the mean average precision of SEER applied to netflat is considerably higher than the general netflat descriptor. Moreover, we can combine SEER also with other descriptors, for example HybridNet or HDZ-delf, and in all cases there is a considerable performance improvement. For the best descriptor, HDZ-delf, we also demonstrate that SEER is considerably better than other approaches for descriptor adaptation from the literature. It is also much faster than the follow-up approach. The representation is indeed environment-specific. It does not work to create the exemplars on Norland and then create the descriptors in a different environment like Oxford. We show in an extensive ablation study that each of the components like sparsity and ensembles are necessary for the performance. We show that SEER is computationally efficient. In particular, for repeated operation in the same environment, the growth of the representation M significantly slows down and more exemplars are reused. We also show that the overall number of operations is only about twice as large as for the comparison of the initial descriptors. Also, the parameter selection is non-critical. We use the same set of parameters for all experiments. And finally, SEER can be used in batch and online scenarios. In particular, it is not necessary to have the complete database available. We can simultaneously extend the database and create the output descriptors, for example for loop closure detection in an online SLAM scenario. Code is available. Please do not hesitate to contact us in case of any question or ideas. We are particularly interested in applying the SEER approach also to other recognition and retrieval tasks.
All right, we're now switching over to in-person speakers. The next talk is sub 1.5 time optimal multi-robot path planning on grids in polynomial time, and the speaker is Teng Guo.
Yeah, hi everyone, my name is Teng Guo. I am a PhD student from Robotics University. Today I will be presenting our joint work with my advisor, Professor Jingjing Yu. We focus on multi-robot path planning on graphs. Given a graph G, a set of robots with start configuration XR and goal configuration XG, we are tasked to find paths for routing the robots from XR to XG. Multiple robots can move along the graph edges simultaneously, but collisions must be avoided. This means that two types of moves are forbidden. Two robots cannot exchange locations using the same edge, and two robots cannot occupy the same vertex at the same time. Usually, the solution quality is measured by some objectives. Here, we focus on minimizing the max span, which is the time it takes to complete the reconfiguration. In this work, the underlying graph is an M1 by M2 grid, where the robot density is ranging from 22% to 100%, which is very high. MRPP finds many real-world applications, including video game, transportation, swarm robotics, and especially warehouse automation. Here are some of the warehouse-related applications where the underlying environment is grid-like. Amazon, Ocado, Jingdong, and other express companies have deployed thousands of robots for fulfilling orders and sorting parcels. These robots essentially run on a grid-like setting. To summarize the result, assuming random XR and XG, we prove that in low polynomial time and with high probability, we can compute 7 to 10.5 asymptotically optimal solutions at 100 robot density, and we can compute 1 to 1.5 asymptotically max-span optimal solutions at up to half robot density or 2/9 robot density with regular obstacles. Our algorithms can scale to over 50,000 robots with sub 1.5 max-span optimality. In contrast, MRPP on grids is strongly NP-hard even without obstacles. Previous best polynomial time big O1 optimal algorithms have very large constant factors. On the other hand, non-polynomial time suboptimal algorithms do not scale very well to large and dense instances. Given the limited time, I will highlight how we achieve the sub 1.5 optimality for 1/3 robot density. To get the optimality guarantee, we first establish a max-span upper bound of M1 plus 2M2 in our algorithms, which I will explain a little bit more in detail on the next slide. Also, we establish a lower bound of M1 plus M2 for the same setting, and when we compare these two bounds, we can get an optimality ratio of 1 plus M2 divided by M1 plus M2. When M1 and M2 are similar, the ratio is about 1.5. If M1 is much larger than M2, the ratio is 1. Overall, we achieve 1 to 1.5 asymptotic optimality with high probability in low polynomial time. On the next slide, I will explain how we achieve the upper bound. To go from XR to XG, we first apply unlabeled MRPP algorithms to both of XR and XG so that each 3x3 cell has exactly 3 robots in it. And then, to achieve the reconfiguration of the augmented start and go configurations, we apply a novel logic table algorithm which says that any reconfiguration of the M1, M2 items in the M1 by M2 table can be realized using M2 plus 2M1 row or column shuffles, where each shuffle can arbitrarily reconfigure a single row or a column of the table. Using the Rubik table algorithm, we can get a set of row or column shuffles which can move the robots between the desired configurations. And then we apply a Harvey heuristic for realizing the row or column shuffles, which is possible at 1/3 robot density. Overall, the maximum is M1 plus 2M2. We implemented all the algorithms. Here on the right, we are showing some of the animations of the computed plan. Note that our algorithm can scale to tens of thousands of robots, where the optimality ratio is still about 1.35. And thank you very much.
All right, very good. All right, I think we have one question in the audience.
Thanks for the great talks. I have a question for the Kernel GPA paper. So I think I probably missed it in the presentation, but what type of regularization did you guys use? And have you guys tested other kind of regularization? Thanks.
The regularization? Yes, so for the RSS, so basically we use the TPS, so in that case we use the embedding energy matrix. And for the RSS, so basically we use the undated matrix. So it's possible to do the other general matrix, but we didn't do that.
Okay, thank you.
Question on this side.
Yeah, I have a question for the last paper, the path planning one. So are you assuming all the robots are the same, or can you deal with different kind of robots with different kind of capability, like speed and others?
So in our work, we assume all the robots are the same. They have the same size, they have the same speed.
Okay. So how about the case when like a robot fail and then the path and everything changes? Can you deal with this case?
Sorry, can you repeat the question?
So for example, in the middle, one robot failed and then blocked the path. Are you able to replan very quickly, or what's your strategy on this?
So in this work, we solved the one-shot multi-robot path planning, and we don't replan the path.
Okay, thank you.
All right, go ahead.
Yeah, sorry, I have another question for the Crow paper. So can you elaborate a bit more on how you go from the projected 2D LiDAR points to the mesh? Thank you.
Okay. When the 3D point cloud, we project them onto the 2D based on the topological relationship for each race shooting in the 3D environment. And when the ray is when each ray is near with its neighbors, we assume that they could be near in the 3D environment. So when we do the 2D projection, it can recover the topological relationship with rays. I think we also open source the code. It could be more easy to understand that part.
Thank you.
Thanks.
I think a good question on this side, and then.
Question for Curl as well. I'm wondering, since in most, I guess, point cloud applications, the point clouds in a grid cell will usually lie on some very thin manifold, but the spherical harmonics seem like they would be better at representing volumes. So I'm curious if why the spherical harmonics are good for representing these thin surfaces.
In the beginning, I explored some papers from computer graphics. So I found out they use this representation to reconstruct models. So I start to think about whether can we use this to represent 3D LiDAR printout. Usually they use it in a small scale model. So we want to make it to work in a larger scenario. So I think I'm not sure whether I answered your question or not.
Yeah, I was mostly wondering about like, when I think about spherical harmonics, it's usually representing volumes, like a closed volume, whereas here in the point cloud case, it's a lot of like very thin surfaces.
Yes.
So I was wondering how you make that work. Are you taking a level surface of the spherical harmonics? Or?
No, I don't think it's usually used in a polar function, 3D polar functions like a star shape. There is no overlap in one direction if shooting from the origin of the coordinate. So it's just directly used for the spherical harmonic function.
All right, I think we'll do these last two questions.
Hello, I have a question for Kernel GPA. So I'm wondering, I see the evaluation is mostly done on one object-centric trajectory. I'm wondering, so if the environment map estimation is generalized well for like multi-object centric trajectory, and the like general trajectory, like general large-scale search from motion scene.
Okay, yeah, that's actually a good question. So currently, we can only deal with continuous environment. So basically, we assume the map to be kind of represented by one model. So basically, if you have multiple objects, like deforming objects in the environment and like kind of severity, so basically we need to, take another approach. So currently, this is basically because of the deformation. The deformation model cannot have kind of multiple objects. So basically, lab part needs a bit more work. Yeah, definitely. Thanks.
Thanks for the answer. So how about like general static things? The estimation map can be generalized well, right?
Sorry, so by means, so what's, I didn't get the point, so.
Yeah, sorry, maybe I can follow up in the process. Thanks.
Okay, yeah.
And last question.
Hi, thank you for the talk. So I have a question for the curl. So the first question is that how robust is the algorithm? Because I saw that you need a denoising process before you convert it into the final representation. So I'm wondering if the input before that stage is very noisy, what will happen to this representation?
For this method, it all depends on I believe the LiDAR printout is the actual representation of our environment. So the only request is if the printout could be denser, the result could be better. If it's too noisy, I think it's just the representation of the real world, so it should be fine. But when we do upsampling there, we did sample some noisy points, and we can denoise very well to remove the wrong points we sampled from the mesh.
I see. Okay, thank you. My second question is that for the second stage of your paper, you are doing a 2D polarization stage to do the meshing. So I'm wondering, so I think the 2D polarization works because you are the input is a 3D scanning LiDAR. So basically, you can do the projection onto the 2D plane. What if there are like points? There will be multiple points on the same ray, so that the 2D polarization won't do the meshing. If that's the case, can you still process the 3D point cloud without any assumption?
I think that's a limitation of our current method. If there is overlap on or occlusion on the same ray, we can't solve that problem yet. We cannot build a very good mesh. Because we would use a sampling from the mesh, we use recasting. So, yes.
Okay, thank you so much.
All right, let's thank our speakers one last time. All right, and we'll move on to our second round of short talks. The next talk is Occupancy SLAM, Simultaneously Optimizing Robot Poses and Continuous Occupancy Map, being presented by Shoudong Huang.
Good morning, everyone. My name is Shoudong Huang. This is a joint work with Liang Zhao and Yingyu Wang. We are all from the Robotics Institute at the University of Technology, Sydney in Australia. So our work is called Occupancy SLAM, and it means simultaneous optimizing the poses and the occupancy grid map. Occupancy grid map is commonly used to describe the obstacles and free space in an environment. When the robot poses are known, we can use the observations to build up the occupancy grid map. And the evidence grid map is a popular method because it's simple to update the grid. The evidence is actually additive, so you can simply add the new evidence to the previous one. In 2D laser-based SLAM, traditional methods use the two-step approach. The first step is to optimize the poses. The second step is to use the poses to build the map. So we ask the question whether this two-step approach is the best or not. So in this work, we propose a one-step approach, which is simultaneously optimizing the poses and the grid map. One of the challenges here is there's no clear data association because the map is a grid map. So we propose to use the continuous occupancy map because using a single value to describe the evidence of grid is not accurate enough. Here we use the occupancy value at the corners to calculate the occupancy value inside the cell for any position using bilinear interpolation. So in this case, only the values at the corners are our variables. So the state vector, including all the robot poses and all the occupancy values at the corners. And the observation information, we sample the laser beams and get the observations along each beams. To build the objective function, we first transfer the observation to the map coordinate frame and then compute the difference between the actual observation and the expected observation calculated from the map. Because the evidence value is additive, we need to divide the map by the number of hits in this case. So this is our observation term. For the whole object function, we also add another term called odometry term and another term called smoothing term. The smoothing term here is mainly used to improve the convergence of our algorithm. So you can see from our algorithm, one key step is we change the weight on the smoothing term. So after some iterations, we will reduce the weight. This is a result using the museum data set, and we can see our occupancy SLAM can get a better result than cartographer. And this video shows more results using other different data sets, and it also shows the convergence process of using this Intel data set. So you can see the weights here is changing after some iterations. Finally, the algorithm converts to a good map. So in summary, occupancy SLAM is the first to optimize the poses and the occupancy grid map simultaneously, and it outperforms existing method. The uncertainty of the map can also be obtained from our algorithm. Currently, we are still keep improving the algorithm to get better robustness and computational efficiency. This is a wonderful result we have. We start from very low resolution map, and after some iterations, we convert to some reasonable result, then we switch to a high resolution map. In this way, the computation complexity can be reduced significantly. Thank you very much for your attention. You're welcome to join my poster to have any further discussion.
Our next paper is a conflict-based Steiner search for multi-agent combinatorial pathfinding being presented by Richard Wren.
Hello, everyone. I'm Richard Wren, a PhD student at Carnegie Mellon, and very excited to share our work, conflict-based Steiner search for multi-agent combinatorial pathfinding. So we have seen multi-agent system emerging in many applications. An important question is to tell these robots where they should go. And very often, these robots need to collectively visit a large number of target locations for the purpose of information gathering or pick and place items. With that in mind, we formulate the following graph search problem called multi-agent combinatorial pathfinding. So the goal is to plan collision-free paths from the start to the goals while visiting intermediate targets. In addition, we also consider assignment constraints. That is, a target must be visited by at least one of the eligible agents, or say capable agents. And we want to minimize the sum of individual path costs in the graph. So there are mainly two related areas. So the first one is multi-agent pathfinding. So multi-agent pathfinding resolves conflict between agents, but very often they ignore the optimal target sequencing requirement. On the other hand, multiple traveling salesman problem can allocate and sequence the target, but they typically do not consider collision avoidance constraints between the robot. And the goal of this work is to bring these two areas in a principled way together so that we can compute solutions with quality guarantees. So our approach consists of three key parts. So first, a joint target sequence specifies the allocation and the visiting order of targets for each of the robots. Given a joint target sequence, we can leverage the existing conflict-based search to plan collision-free path for all the robots. Specifically, if two agents occupy the same node at the same time, then there's a conflict, and we add constraints to forbid either of the robots from using that node at that time to resolve the conflict. Now, how do we obtain those joint target sequences? We solve a k-best sequencing problem. The goal is to compute the k cheapest target sequences, and formally this problem is referred to as k-best multi-depot, multi-terminal Hamiltonian path problem. Currently, in the literature, there is no algorithm to solve this k-best multi-agent sequencing problem. So we propose our approach to solve this problem. So first, we leverage a transformation technique that can transform the multi-agent problem into a single-agent counterpart, which is basically a traveling salesman problem. Then we leverage the existing technique to solve the k-best traveling salesman problem. Put them together, now we can solve the original k-best multi-agent sequencing problem. And by increasing k to k+1, we can compute the next best target sequence when we need during the search. Okay, now the remaining question is, when do we need to generate the next best target sequence? And the answer is when the cost of the current conflict-based search exceeds a certain threshold. And this threshold is controlled by a hyperparameter epsilon that can take value ranging from 0 to infinity. And correspondingly, our algorithm can output solutions that is guaranteed to be optimal, bounded suboptimal, or unbounded suboptimal. Okay, next I'm going to give you an intuitive understanding about how we provide solution quality guarantees. So basically, the entire search process proceeds along two directions, either resolve conflict between the agents or generate the next best target sequence. Along either direction, the search cost is guaranteed to be monotonically non-decreasing. And in addition, the entire search is organized in a best first search manner, so that the first conflict-free solution path returned is guaranteed to be optimal. Okay, and here I want to share with you a gazebo ROS simulation in a warehouse-like scenario. I modeled the workspace with occupancy grid, 4 connected graph, and as you can see, the planned path can direct the robot to visit the target, let the robot take detours to avoid each other, and get them coordinated in dense coupled areas. Okay, and the short message is that our planner can handle up to 20 agents with up to 50 targets with solution quality guarantees. More numerical results can be found in our paper, and our code is also available online. Okay, that's the end of my talk. I'm happy to answer any question you have. Thank you.
Thank you. Our next talk is the traversing supervisor problem, an approximately optimal approach to multi-robot assistance, being presented by Tianchen Ji.
Hi, everyone. I'm Tianchen Ji from Human-Centered Autonomy Lab at UIUC, and I'm very glad to be here to present our work on traversing supervisor problem, an approximately optimal approach to multi-robot assistance. Roboticists have made noteworthy progress on developing trustworthy robot autonomy. However, robots in the real world are still not perfect and may fail out in the field due to harsh and uncertain environments, especially for low-cost robots as shown in these 2 videos. To make it worse, the robot may not be able to recover or resume the task by itself, and the physical assistance from a human is required to continue the robot task. In such cases of imperfect autonomy, a human-in-the-loop design is necessary, where a single human may need to supervise and manage multiple robots. However, optimally identifying which robot to assist in which order is a challenging task for human supervisors. To share the burden with the supervisor, decision support systems have been proposed to provide advice on which robot to assist in which order. Many previous methods approached the assistance problem using an MDP, whose optimal solution is intractable due to the complexity. In contrast, we model the human multi-robot assistance problem as a graph traversal problem, based on which the optimal path can be computed for the supervisor to follow. In details, we assume that the robots are spatially distributed over a field of interest to complete some navigation tasks. And the goal of the supervisor is to rescue any robots that fail so that the overall human-robot team performance can be maximized. If there are no robots to assist, the supervisor can rest in the control center, which is denoted by the house in this figure. Now, in order to plan a path for the supervisor, such as the red lines in this figure, we model the human-robot team as a complete directed graph, whose nodes are the robots, the supervisor, and the control center. Most importantly, we define the node reward of a robot as the expected distance that the robot can travel if visited, minus the distance if ignored by the supervisor. As a result, the node reward will be 0 if the robot is operating normally, and will be a positive number if the robot fails. The edge cost is defined as the time required to travel between the 2 nodes on the graph, which is different from the constant cost in many previous works where the robot's teleoperation is available. Note that the positions of the robots and the supervisor are time varying, thus this problem is a dynamic problem where all the variables depend on time. Furthermore, we define the value function of a path pi as the difference between the total discounted reward collected along the path and the total discounted traveling cost of the path. Our goal now is to find a path for the supervisor that can return the highest value by solving the following dynamic graph traversal problem. However, this problem is intractable because it requires extra information, such as the knowledge of future robot trajectories. To overcome this issue, we approximate the solution to the original dynamic problem by solving a static problem, where the node rewards and edge costs are fixed to their initial values and the discount factor is removed. Such a static graph traversal problem can then be cast as a profitable toward problem, which can be solved efficiently in real time. Under certain assumptions, we also developed a bound on the approximation error, which is a function of the system parameters, such as the number of robots and the field size. We demonstrate the effectiveness of the proposed planning algorithm in the simulation environment of an autonomous farm. To examine the performance of our method under different conditions, we conduct experiments with varying levels of robot autonomy and robot fleet sizes. We compared our method against multiple baselines and shows that the PTP can achieve the fastest task completion time among the 5 methods under all levels of autonomy and all robot fleet sizes. This figure shows the percentage of the field covered over time with different approaches. We noticed that although our method achieves less progress at the beginning of the task compared to the greedy approaches, it does generate superior global performance due to the long-term planning. This concludes my presentation. Thanks for your attention.
All right, our last talk of this session is cooperative multi-agent trajectory generation with modular Bayesian optimization, being presented by Gil-Hun Ru.
Good morning, I'm Gil-Hun Ru, and our work is about generating a cooperative multi-agent trajectory for quadruped vehicle. Yeah, in the cooperative system, vehicles are traversing a complex environment to accomplish the task while avoiding the collision with other vehicles. To find the time-optimal trajectory, we focus on 2 properties of this problem. First, the vehicle can pass through the same position at different times, so the trajectory may intersect. Also, the vehicle only needs to attain this formation constraint at certain position, and they can deviate from the formation to traverse more efficiently. And so to formulate our problem, we utilize the SLAM minimization method. This method uses a smooth piecewise polynomial, which is obtained by minimizing the 4th-order derivative of a trajectory. It consists of outer loop optimization, which determines the time allocation for collision-free polytopes, and inner loop optimization that converts this time allocation to actual polynomial trajectory. So our strategy is to first find the time allocation that satisfies our cooperative planning constraint and convert it into the polynomial with that inner loop optimization. So we first decompose the free space into convex polytopes and find the time allocation of each vehicle on each polytopes. And these are our cooperative planning constraint, which consists of formation timing constraint and individual dynamic visibility and vehicle-wise collision avoidance constraints of trajectory that is obtained from this time allocation. Because of the complicated quadruple dynamics and noisy sensor data, the last 2 constraints are uncertain and hard to model explicitly. So we utilize a Bayesian optimization to find the optimal solution under this uncertain constraint. Bayesian optimization select the next evaluation point with the acquisition function and update the surrogate model based on the evaluation result. We propose a modular structure for surrogate model, and each module approximates the individual dynamic visibility and vehicle-wise collision avoidance. We use a binary Gaussian process classifier for each module. And to further improve the sampling efficiency, we propose a cascade random sampling. So we first generate a candidate solution for 2 vehicles and sequentially add the solution for the next vehicle that satisfy the formation timing constraint. And among this candidate solution we generated, we select the next evaluation point based on this acquisition function. Our acquisition function consists of 2 parts. The exploitation part selects a solution that is faster than current best solution with sufficient probability to satisfy the feasibility constraint. If the algorithm cannot find such solution, it uses the exploration part, which selects a solution on the feasibility boundary that has the largest uncertainty. We applied our algorithm to ideal quadruple dynamics model and simulated environment that include control delay and noisy sensor model. For the simulated environment, we use the multi-fidelity Gaussian process to further improve the sampling efficiency by combining the low-fidelity evaluation. So we first applied our algorithm to the ideal quadruple dynamics model and generate the fastest trajectory that has a feasible control command. And we compare our method with two baseline methods, which use the formation control and mixed integer programming. Since we use less conservative collision avoidance constraint, our method can generate faster trajectory than the baseline method. And we also applied the same algorithm on the simulated environment and generate the time-optimal trajectory that has a certain level of tracking accuracy. Okay. Finally, we tested the optimized algorithm in the real-world environment, and we were able to fly the Ford drone up to 7 meters per second with the centimeter distance with other drones. Okay. Thank you for listening. Feel free to find me during the poster session. Thank you.
All right, we'll invite all our speakers back up for questions. All right, we have a question on this side.
Hi, I have a question for the multi-objective kind of robot fixing paper. Thank you very much for the great talk. Are there any scenarios where the path that's generated for the human to follow are perhaps optimal for efficiently fixing the robots, but are perhaps not the best like for the person to follow, so maybe like zigzag patterns or just something less comfortable, I guess?
Can you actually repeat the question? I can't hear clearly.
Oh, can you hear me? Can you hear me?
Yeah.
Yeah, so are there any scenarios where the path generated is perhaps really efficient for the robot kind of planning problem, but not as convenient for the person, so maybe like zigzag patterns or something like that?
Oh yeah, so I think one of our assumptions is if the robot can make the path, then the human can also like traverse that path. So yeah, like they can share the same path. That's our assumption there.
Okay. Thank you very much.
Yeah, I have a question for the Occupancy SLAM paper. So I'm wondering the choice of the bilinear interpolation. Have you guys tested like some other interpolation methods such as I think bicubic spline interpolation? And if not, is the choice of bilinear interpolation like for optimization, convergence rate, or something else? Thank you.
Yeah, I'm not sure whether I understand your question. The first is about the bilinear interpolation, right?
Yes, I'm just wondering, like, have you guys tested like other interpolation methods such as bicubic?
Yeah, for this one, we just choose this bilinear one, which is relatively simple. But definitely, there can be other interpolation can be used, but we haven't tried yet. So what's the second question?
The second one is just like whether I'm just asking whether the use of bilinear interpolation is for like convergence rate, but you already answered that. Yeah, thank you.
Okay.
All right, I had a question for Richard, the paper on conflict-based Steiner search, which was, so what happens if you have some humans or some uncontrolled agents in the environment? You can either think of them as if some of the robots are adversarial or there's a human there. Could you extend your method to handle that? Are you robust to that? And what would you do in that case?
Okay, thanks. Great question. So currently in this work, we do not consider like uncertainty in the environment or adversarial robots. but I think that's a very interesting area. Like, as far as I know, like in multi-agent pathfinding, there are work that consider uncertainty, and for traveling salesman, I believe there are also work. Then, if that's the case, then I believe within the same framework, with some effort, these two different type of approach should be able to, fuse together to address the new challenge here.
All right. I'm guessing probably people don't want to ask any more questions because it's now between us and the coffee break. So I encourage you to find all of our speakers and come talk to them at the poster sessions, and we can go get some coffee.
do we have the audio? Okay. Hey everyone, welcome back. If folks can make their way over from the coffee break, I guess nobody can hear me. That's okay. Well, our next session is chaired by Andy Zhang from Google.
Thanks, Chris. Hey everybody, next up we have our 2 blocks of short talks. We'll have 5 papers, 5 minutes each, followed by a Q&A session, then another 4 papers, followed by a Q&A session. Our first paper will be Soft Robots Learn to Crawl, Jointly Optimizing Design and Control with Sim-to-Wheel Transfer.
My name is Chip Schaff, and today I'll be telling you about how you can optimize the design of your soft robots. The end product of our work is a system that allows users to jointly optimize the physical bodies of soft robots and their controllers for a given task. We test this system by optimizing pneumatically actuated soft robots for a locomotion task. Our results show that our approach is able to discover novel and high-performing crawling robots within a highly accurate finite element simulation. In physical experiments, we fabricate the optimized design and transfer the learned controller from simulation to reality, and show that the optimized system outperforms a well-studied baseline by a large margin. The problem of optimizing design and control for soft robots is inherently challenging. One reason for this is that the simulation of deformable materials is hard. If you want to accurately model complex deformations, where the relationship between stress and strain, a large amount of compute is required, which generally renders learning-based methods infeasible. The second is that soft robots themselves are complicated. They have infinite degrees of freedom, allowing them to deform in complex ways, and they can be built from a large variety of materials and actuation strategies. This leads to a large potential search space and a tight coupling between design and control. Our contributions to this problem are twofold. First is an efficient RL-based co-optimization algorithm, and second is a technique to speed up finite element simulations across a large set of designs, allowing us to leverage highly accurate physics simulations. Our first contribution has 2 main components. The first is a design condition control policy, which provides fast evaluations to unseen designs. The second is a distribution of designs that maintains a belief over high-performing robots. These 2 components are intertwined, and that the control policy is trained to maximize expected return under this design distribution, and the design distribution is updated towards higher performing designs under the control policy. Continuing the optimization in this way, our approach converges around a locally optimal design and a control policy which is effectively fine-tuned for that design. With the goal of sim-to-real transfer in mind, we want to carry out this optimization within a highly accurate physics simulation. Finite element analysis provides the required accuracy, but at a large computational cost. For example, this simple quadruped scene runs 100 times slower than real time. This is way too slow for most reinforcement learning algorithms, which require millions of transitions to converge. Several approaches exist for speeding up finite element simulations. In this work, we consider the snapshot proper orthogonal decomposition method. This works by projecting the degrees of freedom of the robot into a low-dimensional subspace that well captures a set of common deformations. This can speed up finite element simulations by several orders of magnitude, but it requires a large upfront cost for every mesh. Naively applying this approach is then infeasible because it requires us to pay this cost for every new design we would want to simulate. Our solution to this is simple. First, we create a library of high-quality reduced order parts using the snapshot POD method. Then we can combine those parts in arbitrary ways to construct new designs. This allows us to quickly simulate large sets of designs while only having to perform a small set of model order reductions. In our experiments, we optimize pneumatically actuated soft robots for a crawling task. Our algorithm searches over where to place pneumatic legs around a central body, which pressure regulators to assign those legs to, and the control policy, which produces crawling gaits. Our results show that our approach is able to quickly converge around a small set of high-performing designs. And in physical experiments, we fabricate the top 5 performing designs and show that they are able to outperform a commonly studied baseline when transferred from simulation to reality. Thank you. If you're interested, please come see our poster this afternoon, and you can check out our website and code using the links below.
Next up, we have Moritz Roos presenting end-to-end learning of hybrid inverse dynamic models for precise and compliant impedance control.
So hi, I'm Moritz. I'm going to present our joint work on hybrid inverse dynamic models for robot manipulator. So one of the main challenges of deploying robots in semi-structured environments is robot control. We need robots which are simultaneously precise and compliant in order to work with fragile objects in forceful interaction tasks. Traditional impedance controllers cannot solve this unless we get more accurate inverse dynamics models, which will be the topic of this talk. So the most common approach to learn the inverse dynamics of a robot manipulator are analytical rigid body dynamics models. They are derived from the recursive Newton-Euler algorithm and have relatively few parameters, but overall good accuracy in the state space. However, they are not precise enough to capture all of the effects which are non-rigid. Therefore, we need to augment our rigid body model with additional dynamic effects in order to get a more precise model. In this context, residual hybrid models are of major interest. By extending our trained rigid body dynamics model with a neural network function approximation, we can increase the accuracy of our overall model while maintaining the good analytical prior of our rigid body dynamics model. However, this approach still has two major flaws which we want to address in our work. First, the identification of the rigid body dynamics parameters is a constraint optimization problem, which has several linear matrix inequalities which we need to maintain. Therefore, it's not suited for end-to-end learning of our joint model. Second, the stateless neural network is also not able to capture partially observable and temporal dynamic effects from data, and thus cannot increase the overall accuracy perfectly, with the effects such as hysteresis. Therefore, in our work, we present our solution to those two problems called end-to-end straight recurrent residual hybrid models. We propose a new hybrid model architecture which consists of 3 main components. First, we have a fully physically consistent rigid body dynamics model, which we extend with a stateless Coulomb friction model with linear approximations for low velocities. And additionally, we use a recurrent LSTM, which has internal memory and is able to learn the residual dynamics efficiently from data. Our proposed hybrid model is now trained end-to-end in 2 steps. First, for our experiment, we collect a large data set consisting of 17.5 million data points derived from using trajectories derived for optimal experiment design. We collect all our data on a real robot at 1000 Hertz in our lab. Second, we propose the differentiable barycentric, alternative formulation of the barycentric parameters, which can implicitly guarantee all conditions for fully physically consistency. This allows us to use unconstrained optimization. We are now able to jointly learn all of our hybrid model parameters end-to-end using stochastic gradient descent methods while still maintaining all of the conditions implicitly. To verify our new model architecture and our end-to-end learning, we conduct several experiments on offline torque prediction and on real robot motion tracking tasks. We deploy all our models at 1000 Hertz inside a torque-controlled robot manipulator and test it on several unseen movements with varying controller gains. In our experiments, we're able to show that our proposed hybrid model, as you can see here in green, is able to significantly increase the tracking accuracy of our robot manipulator in contrast to its baselines. Further, we're able to show that it's precise enough that we can even lower our controller gains from traditional stiff gains to compliant ones, while still maintaining a higher accuracy than our baseline models with a stiff controller. This shows that the residual LSTM is able to capture dynamic effects efficiently for data. It can be used for precise and compliant motion tracking. Our other experiments are focused on the end-to-end learning of our hybrid model, where we conduct several offline and real robot tracking experiments to benchmark it against the sequential learning on our real robot motion tracking tasks. We're able to show that end-to-end learning outperforms the sequential learning. So thank you. I'm happy to answer all of your questions at the poster.
Next up, we have Tara Borushaki presenting Fusebot, RF Visual Mechanical Search.
Hello, everyone. My name is Tara Borushaki. I'm a PhD student at MIT, and today I'm really excited to tell you about our robotic system. So when we normally think about robotic perception, we normally think about them using a camera. But sometimes we need them to do something that they cannot, manipulate something that they cannot see. For example, there is an item under a pile, and the robot needs to manipulate it and extract it. So in this talk, I'm going to tell you how we do it. And let me first show you a video. So here, there is a key under the pile, which is a hidden item that the robot is looking for. The robot has a camera, but its line of sight is blocked to the item. Here you can see in the camera view that the item is not visible. Our system is able to locate the key and then purposefully declutter its environment so that it can extract the item of interest, and then when it gets it and retrieve it, it can declare task completion. So in this talk, I'm going to tell you about Fusebot, which is a robotic system for RF visual mechanical search, and it enables efficient retrieval of items in line of sight, cluttered scenarios, and fully occluded scenes. And it achieves 95% success rate in these retrieval tasks. So how does Fusebot work? It uses RFID tags, such as this one in my hand, and these are batteryless UHF RFID tags that are 3 cents. And the way it works is there is an antenna that sends a wireless signal toward the tag, and the tag responds back with its unique identifier. There has been works that shows we can locate a tag using this response with centimeter-level accuracy. So our system sends wireless signals from different locations, and then it enables it to see through the pile and find an RFID tag item to manipulate it and grasp it. But now, the question is, what if our item does not have any RFID? How does Fusebot go and grasp it? So, our system uses RF visual mapping in order to identify what is the probability our item is in each section of the pile. So for example, here is the pile structure in front of the robot, and then these areas are invisible to the robot because they're under the surface of the pile, and it's not visible to the camera. So our system creates an uncertainty model using the voxel grid. These red dots are like high values in our voxel grid, but these are high because our camera cannot see them. But remember, we also have a radio frequency perception. So we have RFID tags here, and then robot can locate them with good accuracy. And then it knows that, okay, here is the toy, and here is the mug, and here is the tape that I was looking for. So it fuses them into the lower, to this uncertainty model, and this area will have lower uncertainty because we exactly know what is there, and what is their shape, and what is their size. So now we have a better understanding of what we know and we don't know. So then, here is the item we're looking for. We create a convolutional kernel based on its dimension, and then we convolve it with this uncertainty model, and it gives us an occupancy distribution. So here, the red area shows there's a high probability that our item is there, and blue area shows that there is a lower probability that our item is there. And this is because, like here, there is an RFID tag item, so we cannot be exactly at the same location. So now we have created an occupancy distribution of where our item of interest is. Now the question is, how do we manipulate this pile to extract it? So we use RF visual extraction policy, which tries to find the item by removing the item that maximizes our information gain. So here is a pile structure, and we segment the items that are on the surface of the pile to understand what are our objects. And then we also have an occupancy distribution from our previous slide. So the robot fuses this segmentation and occupancy distribution to give each of the items on the surface of the pile a mask score. And then it uses the mask that maximizes this information gain if we remove that item. And then, so after it chooses the best mask, the robot goes and tries to grasp this item that has this mask. And it keeps repeating it until it sees the item of interest and can remove it, and it successfully removes it. So we implemented this system in an end-to-end system, and we use a UR5 robot, as you can see here, and we have a camera, an Invariance camera on our wrist, and a locked periodic antenna on a 2-finger gripper. And these antennas are connected towards some wires to a Blade RF software-defined radio, and we have evaluated our system also and compared it to the state-of-the-art vision-based system like X-ray. And X-ray needed a median of 5 actions to find an object, but Fusebot needed 3 actions in order to find it when the item was RFID tagged, and only 2 actions to find the item when it was not RFID tagged. So in this talk, I showed you how Fusebot can efficiently retrieve any item in fully occluded scenarios with 95% success rate. And I'm really happy to answer your question during our poster session. Thank you.
Next up, we have Rohan presenting Learning Interpretable High-Performing Policies for Autonomous Driving.
Hi everyone, I'm Rohan, and today I'll be presenting our work on learning interpretable high-performing policies for continuous control. So say we have an autonomous vehicle or AV operating in a safety-critical domain such as driving around human drivers. This AV is controlled via a decision-making function that receives observations and outputs actions. At the end of the pipeline, we have human operators that would like to receive information about the decision process and could want to calibrate the behavior and choose whether to deploy such a policy. In prior works, reinforcement learning with black box models has been used to produce such policies. However, this does not permit inspection by human operators, and it is difficult to verify such a model. It is instead better to utilize white box approaches that permit insight into the decision-making model. Specifically, interpretable models, i.e. those that provide a transparent global representation of a policy's behavior, can be used to support situational awareness, build trust, and ensure safety. This insight is required in safety-critical and legally regulated domains. However, the ability to optimize sparse logical models, such as decision trees, has been noted by Rudin et al. As one of 10 grand challenges in interpretable machine learning. Our work builds upon differentiable decision trees, or DDTs. DDTs contain decision nodes and leaf nodes. Inside each decision node is a splitting rule, and a sigmoid with steepness alpha is applied to output the probability of a node being true. Leaf nodes contain a distribution over policy actions. We can then compute branch probabilities and multiply these by the respective leaf nodes to produce a final probability distribution over actions. In prior work, DDTs have been trained via supervised learning by Suarez and Lutzko and Pelagia et al., and via reinforcement learning by Silva et al. For discrete action spaces. However, DDT models have been unable to handle continuous action spaces required for domains like autonomous driving. Once parameters have been inferred, prior work utilized a post-hoc crispification technique to produce an interpretable model. This consisted of 3 operations. First, ensuring that each decision node is a function of only one feature. Second, ensuring each decision node outputs Boolean decisions. And lastly, ensuring that each leaf node outputs a single action. While these steps successfully generated an interpretable model, the resultant model was inconsistent with the trained model, as each argmax operation resulted in model differences that can degrade performance. As such, the resultant interpretable model is not representative of the model learned via RL. To resolve this inconsistency issue, we proposed interpretable continuous control trees, or ICCTs. Here we start with a set of input features X. These are passed into a decision node, and we utilize a differentiable crispification mechanism to translate this node into an interpretable node while maintaining gradients. Our differentiable crispification mechanism allows us to directly optimize over sparse decision tree-like representations, ensuring that the output of the interpretable tree is the exact same output as the differentiable model. As the output of nodes are now Boolean, we can trace along a single branch until arrival at a leaf node, which produces a continuous output, in this case, a throttle value for a lunar lander engine. We extend DDTs to continuous action spaces by maintaining linear controllers at the leaves with variable sparsity, going from a simple tree with scalar leaves to a multivariate linear controller. As such, we're able to learn interpretable models that are compatible with models trained via reinforcement learning. To evaluate our ICCTs, we test across 6 domains. Several are common continuous control problems, such as inverted pendulum and lunar lander, while others are autonomous driving domains. In this table, we show several models trained via soft actor critic across the respective domains. In most domains, we see that ICCTs is the highest performing method. In some domains, such as figure 8, we see that we perform a bit worse than an MLP, but maintain much fewer parameters, only requiring a 16-leaf tree with 125 parameters. It should also be noted that the CDDT, an extension of prior work's DDT methodology to continuous domain, greatly suffers in performance when translated to an interpretable model via post hoc crucifixion. In conclusion, we present a framework for interpretable reinforcement learning in continuous action spaces, addressing one of the grand challenges in interpretable machine learning by providing a technique for direct optimization of sparse logical models. In current work, we are working with 4 to transition this for interpretable AV control. With that, I'd like to thank my amazing collaborators, and please do check out our paper. Thank you.
Next up, we have Yoonho Kim presenting Learning Forward Dynamics Model and Informed Trajectory Sampler for Safe Quadruped Navigation.
Hello. In this work, we present our learning-based local planner that enables safe autonomous quadruped robot navigation in geometrically complex environments. Quadruped robots have great potential in our life when they're used with autonomous navigation. However, lots of environments where quadruped robots can be deployed, such as office or subterranean regions, have dense obstacles and make safe navigation difficult. In this work, we are interested in autonomous point-goal navigation in geometrically complex environments. 2D line scan LiDAR was used for the exteroceptive sensor. The state-of-the-art autonomous navigation framework of mobile robots works as a hierarchical system consisting of 4 modules: mapper, global planner, local planner, and a velocity command tracking controller. Local planner that generates velocity command plans to track the coarsely planned path from the global planner is crucial for safe navigation, especially in geometrically complex and narrow environments. In these environments, the local planner should be able to generate long horizon velocity command plans in short time while considering the robot's physical constraints and the performance characteristics of the velocity command tracking controller. Most widely used local planner in previous work is the waypoint-based method that repeats waypoint selection and command generation with PD controller. However, these methods do not guarantee safety while moving toward that point. Recently, there were some learning-based approaches, but the results are limited to single-step planning or not built for global path tracking. In this paper, we present a learning-based local planner that enables safe navigation even in geometrically complex environments. The planner is composed of 3 modules: a forward dynamics model, an online sampling-based model predictive controller, and an informed trajectory sampler. Forward dynamics model is a deep neural network that predicts future base coordinates and collision probabilities given the current LiDAR observation and the future velocity command trajectories. The model is trained with a self-supervised learning framework that repeats random environment generation, data collection, and model training. To generate velocity command plans to track the planned path from the global planner, sampling-based MPC was used. The algorithm repeats command sampling, reward computation, optimization, and first-step command execution. Rewards are computed using the predicted outputs from the forward dynamics model and consist of 2 terms: path similarity term with the global path and the path safety term. Although the local planner using only the forward dynamics model and sampling-based MPC showed decent performance in lots of environments, it frequently failed to find safe command solution in environments with dense obstacles. This was due to the curse of dimensionality in long horizon planning scenarios. To solve this, we decided to learn the command sampling distribution that can generate paths close to the global path and provide rich samples for the optimization. Informed Trajectory Sampler is a deep neural network trained for this purpose. It takes as input waypoints and current LiDAR observation and outputs velocity command trajectories to track the given waypoints. It is modeled with a conditional variational autoencoder, a type of conditional generative model. As shown in the below figure, generated sampled command trajectories from the Informed Trajectory Sampler results path close to the global path shown in yellow. Now we will summarize the proposed learning-based local planner. First, velocity command trajectories are sampled from both random sampler and informed trajectory sampler. Then, forward dynamics model is used to predict the future outcomes of the sampled velocity command trajectories and compute rewards. Based on the rewards, the velocity command trajectory is optimized and executed in MPC fashion until the goal is reached. In experiments in diverse environments, the proposed learning-based local planner showed higher success rate with large gap compared to the widely used waypoint-based method, especially in environments with denser obstacles. To show the importance of the learned forward dynamics model, we compared with the method that runs forward simulation analytically with an approximated kinematic model. Our method, using learned forward dynamics model, showed higher success rate due to lower coordinate prediction error and lower computation time for the forward simulation. The method, using both the random sampler and informed trajectory sampler, showed the best performance compared to the method using only one of them. It was because random sampler can generate diverse samples for exploration, while informed trajectory sampler can provide rich samples and guide toward a precise solution. Furthermore, our proposed local planner can reactively handle unexpected obstacles on the global path and can also be extended to semi-autonomous tasks with minimal changes. If you are more interested in our work, visit our project page and poster session. Thank you.
Great. Let's invite our speakers to come up for question answering. I have a question for Charles, actually, on co-optimization of design and control. So, great talk. And one question is that since you're treating the design distribution as a categorical one, does the number of designs need to stay fixed over time? And is there do you think there are opportunities to expand that dynamically? I think the audio for Zoom is off.
Can you hear me?
Try again.
Can you hear me?
Yeah, we can hear you.
Great. So in this work, we do keep the number of designs fixed, but you can definitely expand upon that. You could dynamically add designs throughout training. There's nothing stopping you from doing that. And you can also use other representations of the design distribution if you so choose.
Cool, thanks. All right, we have a question here.
Hi, I have a question about the interpretable decision trees work. If I have domain knowledge about information I want to have on the structure of the resulting decision tree, what would be the best way to incorporate that kind of knowledge, like whether into the initialization process of the initial tree or during the optimization process?
Yeah, so you can impose structure by initializing it to a certain depth. For example, like you could specify an 8-leaf tree. In current work, we're extending it so you could specify something like an important feature that you would like to see in the tree. So you can, and then you can also specify the sparsity of the linear controllers. So controlling it to be, a multivariate linear controller with 3 dimensions versus 2 dimensions, things like that.
Thank you.
Yep.
Next question on the other side.
Thanks. I have a question about Fusebot. I was wondering whether it might be interesting to also reason about the dynamics. If you take an object from the top of the pile, it probably won't change it much. But if you grasp something from the bottom, it might go rump.
So that is actually being considered for in the mask scoring. So it also, the score of the mask is also dependent on the height of the object on the pile. So normally we prefer to remove something on top of the pile because it then, the possibility of something being visible to the robot after we remove it increases. So that's considered in the mask score.
Thanks.
There's another question for Fusebot. I think I understood this correctly, but you said that picking out tagged objects took 3 motions on average, and picking out untagged ones took 2 motions. So that implies that it's easier to pick out untagged. Sorry, it's easier to pick out untagged ones, which seems counterintuitive. Why is that?
So the thing is that the tagged environment, the experiments for the tag, they're not exactly the same as the untagged. But the experiments for X-ray was exactly the same as the experiments for the untagged objects. So they were run on exactly the same scenarios. But the tagged objects, they were different objects. That's why they were easier, they were harder to extract. Normally, most of them was because we were trying to grasp, and then it failed to grasp, not failed to find it.
Cool, thank you.
Cool. Let's thank our speakers once more. All right. So our next talk will be presented by Xian Xu on meta-value learning for fast policy-centric optimal motion planning.
Good morning, everyone. My name is Xian Xu from Penn State University. Today I will present a paper, My Way of Learning for Fast Policy-Centric Optimal Motion Planning. Policy-centric optimal motion planning is to find a feedback controller which steers the robot to reach the goal region with minimal cost. The robot is governed by a nonlinear dynamics, and the cost is divided as infinite integral of the cost functional. A planning query is corresponding to the configurations of the goal region and obstacles, such as locations and numbers of obstacles. It is characterized by the cost functional L. Once a new query is reviewed, the robot needs to quickly synthesize an optimal feedback controller. However, the problem is challenging in general. On one hand, the robot operates in real time and computation time is limited. On the other hand, computing this kind of optimal global feedback controller is time-consuming. In this paper, we use machine learning to address this issue. Machine learning is to learn amount of knowledge for distribution of tasks, such that a faster learn step based on the knowledge leads to a goal adaptation to a new task. In this paper, we extend applications of the machine learning to fast policy-centric motion planning with nonlinear robot dynamics in continuous time, state, and control domains. Suppose motion planning queries follow a distribution. First, we sample a set of queries from a distribution. For each query, we use the set value analysis to discretize the time state control of the robot dynamics and approximate the optimal value functions on a discretized state grid. Second, the obtained multi-value functions are used to train a microcontroller, which is parameterized by a neural network. Third, the microcontroller is stepped to a new query when the new query is reviewed. The first 2 steps are done offline, for example, in hours and time-consuming. The adaptation is done in real time, for example, in few seconds. Let's see how to train the microcontroller. First, we evaluate the neural network controller by a sum of 2 losses. The first loss is the distance between the output of neural network and the optimal value functions on a discretized set value dynamics. This term enforces the neural network to approximate the discretized optical controller, which is solved offline. The second loss is the residue of the HGB equation, which is the sufficient and necessary condition of the optical controller. This loss enforces the neural network to approximate the solution of the HGP equation, which guarantee it is optimal. So next, we train the microcontroller by minimizing the expected loss of depth controllers, which are updated from the microcontroller by one-step graded descent to a specific query. Therefore, the microcontroller is the best candidate to adapt to queries quickly and with store data. After the microcontroller is trained, it is used to adapt it to a new query. First, we need new data for the new query. For each initial state, the concept-free method solves the BVPs to get the object trajectory and also returns object values and object controls along the trajectory. It continuously solves the BVPs for different initial states, sample the object values and object controls along the trajectory, and add them to the data pool. And each time the data pool is updated, we also updated the parameter of the controller by graded descent on the new data pool. In the experiment, we consider 4 queries with different goal region and different configurations of the obstacles. From the left side figure, we can see the controller can steer the robot to reach the goal region from any initial state. On the right hand side, the figure shows the average cost as the computation time increases. It is shown our method can compute a feasible controller in about 2 seconds and also returns the solution which is close to the optimal controller in about 8 seconds. This is about 10 times faster than other policy-centric methods. So this is my presentation. Thanks for attention.
Next up, we have Yanlai Yang presenting Bridge Data, boosting generalization of robotic skills with cross-domain data sets.
Hi, everyone. We present Bridge Data, boosting generalization of robotic skills with cross-domain data sets. The prevailing paradigm of robot learning is to train a single task in a single environment and throw away the data afterwards. If we instead collect all this data and effectively reuse it, we could significantly boost generalization. So how can we enable robot learning researchers to use past data? In computer vision, large reusable datasets like ImageNet provide good initialization on fine-tuning for other tasks. But robotic datasets tend to be lab and task-specific. Therefore, we propose to gather a large multi-task and multi-domain dataset, which we call the bridge dataset, such as someone could use the dataset to boost performance of their own task in their own scene. To this end, we collected a large dataset of a robot performing a wide variety of kitchen tasks in many different toy kitchen domains. We call this the bridge dataset, since it allows us to bridge the gap between tasks and domains. We focus on kitchen-themed tasks, as these provide a large repertoire of behavior and use a low-cost WidowX robot arm to maximize accessibility. Our dataset contains 7,200 human demonstrations from 71 tasks across 10 different toy kitchen environments. In this presentation, we focus on 2 different problem settings. One is generalizing a task that exists in the prior data to a new target domain where we only have some data for other tasks. We call this zero-shot transfer with target support. We hypothesize that by leveraging the bridge dataset, some tasks can be zero-shot transferred to the unseen target domain. The second one is learning a new task that is not in the prior data in a new target domain. We hypothesize that we can use the bridge dataset to boost generalization of new tasks in new target domains. To test these hypotheses, we consider the multitask imitation learning setting. We will train a neural network end-to-end on both the bridge and a small amount of target data to infer the robot actions from camera images and a one-hot task encoding. Next, we present the results. In the first scenario, we test whether we can transfer tasks in the bridge data to a target domain where we only have a small amount of target data on other tasks. We compare the success rates of policies trained on bridge data only, which we call direct transfer, with policies jointly trained on both bridge and target data. We can see that the success rates are significantly higher when using joint training compared to direct transfer. In this example, we run a multitask behavioral cloning policy that was trained exclusively on bridge data. The policy fails to generalize to the unseen target domain. With joint training on both bridge and target data, the policy is able to successfully execute the task, which has only been demonstrated on other domains in bridge data to this new target domain. In the second scenario, we test whether we can use bridge data to boost generalization for a new task demonstrated in the unseen target domain. We compare performance of policies trained only on single task target domain data with joint training on both bridge and target data across 7 different tasks. We confirm the hypothesis that joint training on bridge data is crucial for the generalization capability of the policies, leading to a more than 2x performance gain on average compared to only training on single task target domain data. Here, we attempt to learn the wipe plate with sponge task in a new real kitchen environment with only 50 demonstrations. A policy trained only on the target domain exhibits poor generalization and fails in most configurations. With joint training, the policy is able to reliably complete the task, even though the sponge object was never seen in bridge data. To summarize, we showed that a multitask, multi-domain bridge dataset can boost policy generalization of new tasks in new domains. Jointly training the bridge and target data allows transferring other tasks to the target domain in zero shot. The dataset and the code is open source. Please visit our website and poster for more information. Thanks.
Next up, we have Takuma Yoneda presenting invariance through latent alignment, and this is remote.
Invariance through latent alignment. I'm Takuma Yoneda. This is a joint work with Ga Yang, Matthew Walter, and Bradley Study. When we take a learning-based approach to robotics, it is common to train an agent in a local simulator and deploy it in the real robot. It is often the case that the agent works well in the source domain it is trained on, but not so much in an unseen target domain. This is because there is a distribution shift between the domains. In a sim-to-real setting, this can be caused by factors like these. So how do we solve this distribution shift? A typical approach is data augmentation. As you can see, the discrepancy between the domains causes distributions to mismatch. Data augmentation expands the support of training distribution with synthesized data, hoping to cover the test distribution. However, as we don't know what a test distribution looks like during training, it is often impossible to sufficiently cover test distribution by this scheme. On the other hand, adaptation modifies the projection from input space to the latent space so that the distributions in latent space will look similar. This approach has a potential to work with largely deviated test scenarios. Here's the problem setting we consider. There is a policy that works well in source domain, but it doesn't work well in target domain. We want to perform adaptation on this policy so that it works well on target domain. We have access to trajectories in both domains. We assume that trajectories are not paired, meaning that there's no corresponding frames. And that reward is not available in target domain. These trajectories don't need to be expert trajectories. Indeed, in our experiments, we use random trajectories. Now, let me describe the method we propose, invariant through latent alignment. As a preparation step, we first deploy a random policy in a source domain and collect random trajectories. For each frame of the trajectories, we encode it and store the latent transitions to a buffer. This encoder is a part of the pre-trained policy. After storing latents, we move to adaptation step. First, we sample a latent from source buffer, and in the same way, we encode a frame from a random trajectory in a target domain. Then we jointly train a discriminator that takes a latent either from source or target. This adversarial adaptation scheme encourages the encoder to produce target latent that is indistinguishable from the source latent. In addition to this, we further guide its adaptation via a forward and inverse dynamics model pre-trained in source domain, which we call dynamics consistency. In experiments, we have evaluated on 3 types of distractions in DeepMind control suite domains: color, background, and camera pose distractions. We also varied intensities of the distractions to see how that affects the performance. Comparing with various baselines on the performance before and after the adaptation, we could see that our method helps preventing the performance drop against distraction intensities. We also experimented on a simple real setting on a reach task. Simulation is on fetch robot, and real is set up with URL5 and a table with distracting texture. In this experiment, we could again show the effectiveness of our approach. Thank you for your attention.
Our last talk for this block is Correcting Robot Plans with Natural Language Feedback, presented by Pratyusha Sharma.
Hello, everyone. I'm going to be talking about our work on how natural language can be used as a tool for correcting and updating a robot's behavior at test time. Consider a robot that knows how to scoop ice cream. While most of the time the robot might give you a nice scoop of ice cream, it might fail at times due to changing environmental factors. For example, what if the brick of ice cream is harder than usual, or if the container is slippery, or both? The robot may fail because of not applying enough pressure while scooping or not holding the container tightly enough. What if the user wants chocolate chips, which are only scattered to the extreme right of the bucket? In all of these cases, how might one update the robot's behavior to changing conditions or new incoming user preferences? In fact, such situations might arise in the lab too, where the robot might go dangerously close to fragile objects while performing a task. Concretely, a good planner can fail to complete tasks or respect constraints due to distribution shifts, modified user preferences, or planner failure. So what does it take to fix all these things today? Typically, an engineer has to go back into the code and rewrite the cost function that has been specified by hand, and this isn't feasible for ordinary users. When people work together to perform complex tasks, we have a much better tool for modifying plans on the fly: language. Language is a concise and descriptive system that allows us to index a wide set of factors of variation. It also allows referring to a range of abstract concepts that may require several demonstrations to convey otherwise. And this talk is going to be about bringing this ability to robot systems and use language to correct, constrain, and modify plans at test time. There's been a lot of great prior work on fixing robot behaviors with corrective feedback of various kinds, like a joystick or kinesthetic demonstration. There's also been work on using language to provide feedback to policies, But past work has focused on using language corrections as the new goal specification. Here, we are instead going to develop techniques that let us change goals, but also selectively add constraints or modify select attributes of existing goals. So how do we do this? A robot's objective is a composition of several costs. For lots of motion planning tasks, plans come from running a planning algorithm like RRT on a cost map that looks like this. Of course, costs can operate in more complex spaces. We can put costs on velocity rather than position or vary them in time as well as space. The cost function can be composed of various terms such as goal-reaching costs, collision avoidance costs, and so on. And a lot of these are task agnostic and be written as other costs. In addition to these costs, we introduce a residual cost term called the feedback cost. We want to be able to use the feedback cost to both add constraints but also change goals, and we do this via a simple switching mechanism where the goal cost is turned off only if it is predicted that the feedback given is associated with a change in goal. Therefore, both the switching and the residual feedback cost is what we learn. So a natural way to use language is to modify planning behavior by mapping natural language strings to cost functions, and the function additionally conditions on the robot and environmental state. We train a neural network to map these inputs to the residual cost map, and this cost is then added to the remaining robot costs, and the planners used to roll out the trajectory. To train the feedback cost estimation network, we procedurally generate diverse environments, and the natural language instructions are generated by templating sentences with different interesting linguistic variation, and we train a single model across all these different expression types. We test on held-out virtual environments and tabletop setting in the real world with unseen language instructions, objects, cluttered scenes, and object poses. In action, it looks something like this. The language correction model conditions on the initial state of the robot and environment and instruction and generates a cost map. This cost map, in combination with the robot's other costs, is then used by the planner to roll out a trajectory. To connect this back to the early example, this now allows us to, on the fly, update a robot's behavior to avoid fragile objects and glasses. So here are some results. So language feedback allows the application of a single correction to multiple environment types at once. This is in contrast to how correcting via actions allows making fixes one data point at a time. It allows the specification of abstract feedback types, such as asking the robot to stay away from the box of Cheez-Its. It allows controlling a variety of features, such as speed, position, etc., on the way to accomplish the task. And finally, it allows composing multiple natural language feedback at once, such as asking the robot to stay away from the box of Cheez-Its while also going slower. Okay, so in conclusion, we propose a new method for correcting robot plans from natural language feedback by learning a language parameterized additive cost term. And this lets us correct, constrain, and modify planner behaviors at test time. Thank you, and if you're interested, please check out our poster this afternoon.
Great, let's have our speakers come up for the Q&A session. Looks like we have a question on that side of the room.
Hi, I have a question for the second paper, the bridge data. So I wonder when you do the new task, how does it work with the one-hot encoding with the task? Because I saw that you have a one-hot encoding for the task to go into the network, right? So for a new task, how does that work?
Since we are joint training on both bridge data and the new task, so we can just add another task ID for that specific task that is not in the bridge data.
I see. So the number of source tasks cannot be like, for example, you have a one-hot vector for 32, so you cannot go beyond. Like, for example, you cannot have 32 source tasks in order to transfer, right?
Yes.
All right. Thank you.
We have another question on that side.
Yeah, hi. I have a question for the talk Invariance through latent alignment. Great talk. I was curious how, what in your loss ensures that the objects with the same pose but different backgrounds map to the same point in the latent space?
I think I couldn't partially hear the question. Was the question
what makes sure the same pose with different background projects to the same point?
The same point in latent space. Yep, exactly.
So, yeah, if we only do the adversarial adaptation, there's no guarantee in a sense. But we have, in addition to that, we have this forward in inverse dynamics, which is pre-trained in source domain. So that kind of encourages to retain the state action paired in a local space of the latent. So that, I can't say guarantees, but that encourages to have the consistency.
Great, thanks.
We have time for one more question. We'll take it from that side.
Okay, actually, my question is following the previous question. And so in the latent alignment, do you have any particular consideration for the structure of the latent code? Or, yeah, how do you represent the latent code?
Excuse me. So the trick is we have access to a pre-trained model, which is pre-trained in a source domain, and we assume that pre-trained policy consists of, and the policy part conditions on the latent, which is the output of the encoder, and we are essentially adapting the encoder part. So the latent is given by the pre-trained encoder.
Okay, so do you have any particular consideration for the encoder structure?
I'm sorry, conservation?
The structure of the encoder. You mean the latent code is generated from the encoder. And do you have any consideration for the design of the encoder?
Oh, so encoder is just a simple CNN, so we didn't put any weird stuff in the encoder.
Okay, thanks.
Was that the question? Yeah.
All right, let's thank our speakers. And that's the end of this block.
Well, we might want to just sit down there first and then come up after the talk. Oops, what's going on here? I thought this was going to work right off the bat. Okay, let's try this again. All right, so our next session is a real treat. It will be hosted by Gaurav Sakatme. It's the Test of Time Award and panel. Gaurav, take it away.
All right, let's see. Is this good? All right. All right. Thank you very much. So yeah, this is indeed a treat for a session. This is a special session that RSS introduced 3 years ago. And it's the practice at RSS now to give a Test of Time award to a paper or group of papers that appeared at RSS at least 10 years ago. And so it's my great pleasure to announce that the Test of Time award today goes to this pair of papers, incremental sampling-based algorithms for optimal motion planning that appeared at RSS in 2010, and the follow-on paper, sampling-based algorithms for optimal motion planning that appeared in a special issue of IJRR shortly thereafter. The authors of these two papers are Sertac Karaman and Emilio Frazzoli. And let me read out the formal citation for the award. The award is given for the first formal asymptotic analysis of the quality of stochastic sampling-based path planning algorithms and the introduction of new, provably asymptotically optimal algorithms, PRM star and RRT star, in wide use today. So please join me in congratulating Sertac and Emilio on this prize. I'd like to thank everybody who worked on shortlisting papers and nominating papers and arriving at the final decision. It's incredibly important to us as a community that we select papers that really truly have had an impact on our way of thinking about robotics. In that spirit, what we will now have is a short lecture by the awardees. I believe Sertac is going to give the lecture today, reflecting on this work. And this will be followed by a panel of experts who work in the area who will reflect on what the field was like before this paper or a couple of papers were published and what has changed since. And so it's an opportunity to celebrate sort of what sort of a marker these papers laid down and what impact they had on our field. So I invite Sertac to now give us his lecture.
Okay, thank you so much, Guaro. I tried to share my screen, and I hope that's visible and people are hearing me okay. I'll keep going unless I hear otherwise. So I'd like to first say that we're just incredibly excited, honored, and humbled for this award. We thank the community for seeing value in this work and giving the award to us. Again, extremely excited, honored, and humbled. And I apologize, neither of one of us could make it in person. We were not hoping to travel, and we learned the award very recently. And I got a chance to join remotely, and I really thank the organizers for accommodating us in this way. And I thank you all for accommodating us in this way. I'll be able to join remotely and do a short little talk, as it was mentioned. Unfortunately, Emilio will not be able to make it at all, but hopefully it'll be okay. So I should say that the organizers asked me to talk about mainly our paper and its making, and I'm not going to go into the follow-on work that was done by many others, in particular those on the panel and some of the others. I understand the panelists will talk a lot about that, so I'll just kind of focus a little bit on our paper and present some fun things about it. Admittedly, both Emilio and myself, we kind of a little bit moved on after this paper to research other topics. It's for many reasons, not that we weren't excited, we were actually extremely excited. It turned out that we both kind of started two separate companies and we actually, within those companies, we worked on these things in their applications, and they were both acquired by sort of competing tier one suppliers, and they still compete in the Boston ecosystem today. Now as a part of these suppliers, and we're actually not anymore a part of these two companies. So again, I'm gonna just tell you a few fun remarks of the making and leave the other work to the other panelists who've done very valuable work themselves, and I'm sure we'll cover the rest of the literature. So, to me, I think at the very least, this kind of work started with the DARPA Urban Challenge. So I had just finished my sort of undergraduate degree, and I had a lot of mathematics degrees of all different kinds, starting almost from primary school. And I kind of was looking for an advisor at MIT, and Emilio told me about this project, and I thought that finally a chance to build something as opposed to proving things. And so I jumped on it. Admittedly, I realized a little bit later that I think Emilio admitted me to his group largely because of my mathematics degrees, not so much my excitement on this kind of applied projects, but later on it turned out really great. We were a very small part of a very large team doing the DARPA Urban Challenge at MIT. So here's a team photo. I wish I had a better resolution version of this. You can find me and Emilio in this picture. We looked very different a decade and a half ago in 2007. So right behind Emilio, or a little bit behind Emilio, you'll see Seth Teller, who was leading the perception team. Right next to him, you will see on his left, you'll see John Howe, who was leading the planning and control team. And right next to him, you'll see John Leonard, who was leading the whole effort. In this very picture, actually, there's a lot of friends and a lot of people out there in the community. On one side, for example, you can see Ed Alston. Right behind Emilio, you'll actually see Matt Walter. And there's many others that I'm not going to go into that became friends over time. What we ended up doing is, when we started the Urban Challenge, we don't have much experience. We just got like the biggest vehicle out there. It was actually donated by Land Rover. And then, we did a variety of things to make it autonomous back in 2007. This is a video taken by John Howe. So the car will come over and will turn around, and you'll see actually there's nobody inside it. So it's driving itself. For us, what really happened is that to do the motion planning here, we used the RRT algorithm. This was back in 2007. So here you're seeing the RRT algorithm execute a parking maneuver. On top, you'll see the left, center, and right camera views. And what you're seeing as the map is, the perception team gives us this, the black area is a drivable region, red are the obstacles, roughly speaking. You see a white tint that's a little bit the cost of being in places. And then we're supposed to plan on that. And so you've seen the vehicle is just parked, and now it's going to unpark and go to another location. And the hairy thing that we're seeing is the RRT trajectories. And so it's planning to go back up a little bit and go forward and go to this location. So it was a bit of an eye-opener for us that we could build an algorithm. Admittedly, we had to put a lot of tricks into it. And I personally haven't even worked on the main variables of the RRT algorithm, except just debugging it slightly on this particular project. But it was a an eye-opener that you could build one algorithm and get a lot out of it. In fact, it came out actually in one of the examples. So here's an example that we came up in the Urban Challenge. I hope it's streaming fine. We come to a four-way stop. So we come and stop at an intersection. We came first. Another robot, which I'm not going to name, comes up a little later. It's stopping too. Now it's our turn to go. Admittedly, we wait a little bit, but we then generate our trajectories as expected. And so we're going, and that robot starts to move all of a sudden and cuts us off. And the fact that we're using an RRT algorithm here, we have a whole bunch of paths in our tree. We're always thinking about how we can come to a safe stop. And so we actually end up stopping on time, turning around and collecting ourselves and completing the turn, even though we got cut off. And so these kinds of examples started to make us think that these are actually really amazing and awesome technologies that we should really be building on, and we could do a lot with. And so at least my interest in this, and I'm not going to speak for Emilio, this particular challenge really made me think that there's a lot here that we can work on, and these things could be part of real systems in the future. Overall in the race, we did pretty okay. We got into a couple minor incidents, but otherwise the vehicle performed just fine. As I said earlier, the motion planning was just a part of it, and frankly, myself and Emilio were a very small part of the whole motion planning team. And there's a lot of work that went into perception and other things to make it happen, but it was exciting for us to see that we could make this work. Right after this, we worked on another project. This time it was led by Seth Teller. So we thought that, well, fully autonomous driving on the roads is probably a couple of decades away. So maybe we should work on other things that are maybe in a little bit more closed environments and maybe a little slower speed, a little easier. So we decided that we built like an autonomous outdoor forklift. It was quite an exciting project. It was led by Seth Teller. You can see Seth in the jacket in the front, and I'm of course right next to his right. You can see myself. And this particular project, really the whole technical effort was led by my friend Matt Walter, and I was leading the more planning and control tasks. And so working with Matt on this effort. We had the whole planning algorithm in the Urban Challenge, so we thought that we just take that and bring it here, and it's a very similar vehicle. There's some subtleties, but it should work fine, right? So day after day, we started to work on this. Simple tasks were easy. So this is the fully autonomous forklift. You could take a megaphone and yell at it, come to receiving, which happens to be an area where trucks pull up with pallets on it. So the whole thing would navigate over there, and then you could see the pallets. We had a Nokia handheld tablet. I don't know if you guys remember that company. You could just circle a pallet with a stylus, and then the vehicle would go pick that up. I'm not going to go into all that detail, but here in this open environment, we're just using the RRT algorithm to basically just go around, and that worked just fine. Not everything is that great though. So here's an example of one of the things that happened quite a bit. So I'm going to stop this video here. So you can see the front camera of the forklift. There's a truck that's right here on the side. So the right thing to do is to do exactly what the vehicle is doing. You need to go around and turn left to line up with the truck so that you can pick up a pallet. So now there's a bunch of obstacles on our right, and they show up here, and we discover them as we go forward. We have the laser rangefinders, and they see them as we go forward. And as that happens, it ends up kind of making some of our trajectories either infeasible or too costly. So we get rid of those trajectories. So we think that we keep sampling, so we'll find better trajectories, right? But what happens is that we find this trajectory, which doesn't look that optimal, but it's a feasible trajectory. I mean, there's nothing wrong with it in terms of feasibility. It just does a weird loop and lines up with the truck. Unfortunately, once we find this trajectory, it's very difficult for the algorithm to explore other options in different homotopy classes. It seems like it just finds this and it traps itself unless you trash the whole tree and rebuild it. It seemed like it's very difficult to find these examples. So now we've engineered a lot of sampling methods, then we've engineered kind of ways of deleting parts of the tree and rebuilding, but really couldn't find much efficient things. To me, they were working fine. I don't know. It seemed like, as I was telling you, I was working with Matt Walter at the time. I think it was fine by Matt also, but not fine by Seth so much. And so we would constantly get emails like this from Seth Teller, it'd say, thank you guys, looks really great. What an awesome work. And except, why does that go that kind of drive forward and turn right? It's just for an unknown reason. Why does it do that? So in some ways, he just kind of kept pushing us to look for a reason. I think this a little bit motivated us to then, so this project went on from 2008 to 2010. So near 2009, it motivated us to look at, so what are some of the fundamental reasons that these kinds of things are happening? So now I should say that algorithms like RRT and PRM, they're actually excellent algorithms. Their designers envisioned them for a solution to a problem where you're looking for a feasible path. The goal isn't to find an optimal path at all. And they're actually extremely good at finding a feasible path. But then the kind of proof we have in the paper shows that they're so good in some ways that if you keep sampling and if you keep running these algorithms, you will not see better paths emerge. In some ways, they're so good at exploring the environment that they kind of trap themselves very quickly, in particular for the RRT, that you will not see better paths kind of emerge out of this. So in some ways, the designers of these algorithms envisioned them to actually find the path quickly. It was kind of a little bit our mistake to think that we're just going to keep running them and get better paths along the way. And as we're looking at sort of, proofs to either kind of make little subtle changes to make it converge to an optimal solution, or maybe even prove that it's not optimal, as we're looking at that, we discovered this whole literature of random graphs. So let me tell you a little bit about this, the kind of things that we ended up seeing that I think were known actually to some of the people in robotics, but maybe not so much publicized or so much kind of maybe investigated. So here's a very simple model, as simple as it goes. You have n vertices, and each possible edge, there's n square edges, including the self edges. Each possible edge is present with probability p. It is completely abstract. There's no topology. These vertices aren't lying on some green space or anything like that. Vertices exist, and you connect them with probability p. And here is a result that is stated very simply. It is quite difficult to prove, actually. But it turns out that this graph includes a unique giant component. Giant component meaning the component has a fraction of all the edges, a constant fraction of all the edges, when the connection probability is greater than 1 over n. And there's no giant component whatsoever. So there's no component that has some fraction of the edges. All components are very small, and they get vanishingly small as n goes to infinity when p is less than 1 over n. This change, there are two remarks here. This change is very sudden. So if it's a little bit over 1 over n, in almost all cases, when n is reasonably large, in almost all cases, you end up seeing the unique giant connected component. It's one component like that. And if it's just a little bit less, in almost all cases, you just don't see it. And there's similar results for connectivity also. If it turns out that p is actually larger than log n over n, which is not that much larger than 1 over n, but if it's larger than log n over n, you get that you connect to all the vertices if n is large enough. And some vertices will always be disconnected if p is less than log n over n. And again, this transition happens very quickly. it turned out that there's a whole mathematical physics literature that is built on these results. This particular phase transitions, it turns out that they actually describe certain kinds of physical phenomena that exists, and mathematicians have studied these models to death in some degree. So this is not exactly what we were working on, but we quickly realized that there's models that are very similar to ours, studied by mathematical physicists who are completely unaware of sampling-based motion planning. And we maybe know of them a little bit, but haven't quite investigated to depth what they can offer. So here is a model. This model was studied for a long time, actually, well before 2003, but I'm going to cite one book by Roger Penrose that was published in 2003. The book is called Random Geometric Graphs. So you have n vertices sampled in a Euclidean space, so this could be like a d-dimensional hypercube, and each vertex is connected all others within a distance r. So you can imagine there's a ball of radius r, and if it's within that ball, you connect to that vertex, right? So I'm going to state these a little bit more precisely. There's some stochasticity in the process, but what turns out is that there's some sort of a critical threshold called at lambda c. And if the volume of your ball is greater than lambda c over n, you get a giant component almost surely as n goes to infinity. This means that as n goes to infinity, no matter how unlucky you get with your sampling, as long as you're a little bit larger than that continuum calculation threshold, you get a giant connected graph. And this is an if and only if statement. So if you're a little bit less than that, then you get no giant connected graph. Seeing these, we just started simulating these things, and it's just fascinating. You can make that just a tiny bit larger, and you almost always get it with even just 100 vertices. And you can make it a little bit less, and you get it with most of the time, again, with 100 vertices. If you have thousands of vertices, like we always have in most of the motion planning problems, you're almost guaranteed. The same thing applies to connectivity also. You get, almost surely a connected component if the volume is larger than log L over n, and if it's less than log n over n, you always get some disconnected little bits and pieces here. Models are the same. What they study is seemingly very different. But if you think about it a little bit, this looks a lot like actually probabilistic completeness. So if you have a giant component, you would, and it has a fraction of the vertices, it may be going around some little bits and pieces, but it should be able to connect anywhere to anywhere else, pretty much, maybe. And this looks a lot like some form of an optimality. I mean, if you can connect to all the vertices, and if those connections are efficient, you can show, it feels like you should have, a path from everywhere to every other place, for example, in a PRM-like algorithm. These are not immediate, but they're not too far either, admittedly. So for example, we started then seeing that going back all the way to 1961, people have looked at models like the PRM. So now, frankly, people who study the PRM, they study something very different, right? I mean, it's just the model is the same. What they study is seemingly very different. But you can see that, similar things, similar models show up in different literatures. Same thing even with the RRT. So a little bit after the publication of the RRT, people got really excited about ad hoc networks, like wireless networks, and they thought about something like the RRT as a model for ad hoc networks. They said, oh, you put in a sensor, and of course, it connects its nearest neighbor. So let's study this network. And so people actually studied these things quite, extensively. And our proofs ended up building on top. And I would say that probably, I think that the one contribution of this paper really is to see that there's this connection. And I think once you see the connection and kind of study how people study random geometric graphs, you can then carry over some of the results and kind of try to make the connections. And then we ended up sort of coming up with these algorithms that we call PRM star, RRG, and RRT star, that we could show that if you actually ensure that there was a connected component, then you should get asymptotically optimal algorithms if you keep running these algorithms for forever. So now I have to admit though that and we admitted this even at the presentation of our main paper, that there actually really is no free lunch. And so you could pretty easily show that the convergence rates of these algorithms show that if you wanted to look for an optimal solution, it could be anywhere in the state space. So you need to really pour samples into the state space. But this is an efficient way of kind of pouring all those samples. So you're kind of taking log n times n extra time, which you are actually taking that already when you were, for example, sampling when you were computing nearest neighbors. So asymptotically computing a nearest neighbor takes n log n time. Now, again, computing a nearest neighbor, constant factor times will be a lot faster, admittedly, than doing all the other things that you need to do here. But we still thought that it was a very exciting connection to see that these two literatures come together. And just luckily, it happens to be that log n times n is exactly the amount of extra computation that you need to ensure that you have optimal paths, for example, in a PRM. And you're already doing that much by computing like nearest neighbors and things like that. And so then, it led to, I think, this movie, which I think captured many people's attention, where you run the RRT on one side, you kind of keep running it. As I said earlier, you don't want to do that. It's designers that intent for you to do that. But hey, you keep running it. And then on the other side, you keep running what we kind of propose at RRT star, and you can see that it's kind of, improving some of the paths without, obviously with some extra effort, but hopefully not so much. And then we kind of got a chance to apply it to some other problems. So here we kind of applied it to a 7-dimensional kind of, I would say, a full model simulation of a vehicle, of a car, a road vehicle, where you can see it's coming and, turn, skid, hit the inner part of the curve and go and hit the outer part of the curve, where like things like race car drivers do were coming out from the algorithm naturally. And then we, of course, went back, myself, Matt Walter, some of the others, Emilio included. We applied it to the kind of problems working with Seth on the kind of robots that Seth was interested in. Certainly looked at autonomous driving compared with just kind of what you would call like a vanilla RRT versus kind of the RRT star, as well as, kind of running the RRT algorithm on a what we had as a PR2 robot versus the RRT star. So we kind of get a chance to demonstrate in these kinds of problems. And then many things happened afterwards, after we kind of published these things. And as I said earlier, I'm not going to go into those. So for the 25 minutes that I had, I'm getting to the end of it. Instead of going into what happened afterwards, which the panelists will do, I'd like to end with this slide. And so we are, as I said, very excited, very humbled by this award. We really thank the community for seeing this award for us. We'd like to take this moment to dedicate this award to the memory of Seth Teller, who frankly is behind a lot of work that has happened at Robotics during the time that he was present with us. He has always challenged us to do better, so we thank him for that, and he is dearly missed. Thank you so much, everybody, for being here, for seeing this award for us, and listening to this little presentation. Thank you.
Thank you so much, Sertac, for a absolutely wonderful lecture. And thank you so much for connecting us not only to the origins of the work, some of its history, but more importantly, perhaps some of the people who were instrumental in making this work come together. So we're really deeply appreciative for an absolutely wonderful talk. So what I'd like to do now is to invite the panelists to come join us on stage. And so Kostas, Dan, and Chris. And so what we'll do is we'll have the panel, I think the panel would probably like to begin by making a presentation, if I'm not mistaken. So maybe we'll have the panel sort of begin with the presentation. I think Kostas is going to lead us off, and maybe the others are going to jump in as appropriate. I'll step away and have the panel kind of have their say. And then if we have time at the end, I know we have a hard stop at 12:15, but if we have time at the end, maybe we can have some questions as well. Right? So Kostas, it's all yours.
Let me see if I can connect first.
Oh, they have mics
on this, actually.
Ah.
To use this. Okay, let me change the change it over.
Do you guys want another?
Great, thank you. Yeah, let me give you a little bit some reflections on Sertac's and Emilio's work from the perspective of someone that was working in the sampling-based community around the time that their paper came out. And this line of work on sampling-based algorithms, started in the mid to late 90s with the introduction of the PRM and the RRT, which led in the beginning in a lot of analysis work of trying to understand the properties of these methods and the underlying motion planning challenges that focused on the feasibility, right, and the properties that people were aiming for were probabilistic or resolution completeness. And there was a lot of excitement, and then these methods were applied in interesting domains. At the same time, during, from 2000 to 2010, I think the vast majority of work actually focused on more heuristic approaches and tools for practical efficiency. I think every research group in the area had their favorite way of sampling nodes and their favorite way of connecting strategies that were kind of engineered approaches that perhaps were useful for some of the applications. There were some, some efforts on generating better quality paths, but let me use a quote from one of the top groups in the area at the time, from Mark Overmars's group, from one of their papers, that said, connecting every configuration on something like a probabilistic roadmap to all of its neighbors results in the best graph and thus the shortest path. But the price to pay for the increased running time is huge. And this shows, that we didn't have yet an understanding for the conditions and the requirements for optimality, and also that, there was the expectation that this is a computationally expensive problem. And, from the practitioner's point of view, you may have seen this comic from the PhD comic. Jorge Cham, he visited Willow Garage in the late 2000s, and, he saw the PR2. PR2 is a robot that was using sampling-based algorithms, and, he made this snarky, a comment, his path planning may be suboptimal, but it's got flair. And one reason I think that he did that is because he visually observed the suboptimality of the methods that were deployed at the time. But then in 2010 at RSS, I had the pleasure of being in the audience in Zaragoza and listened to Sertaç's talk. We learned some things, as Sertaç pointed out. We learned the minimum computational effort needed for sampling-based planners to asymptotically converge to optimal paths under some mild assumptions and reasonable assumptions. And we did gain those insights and the connection between this literature and the random geometric graphs and percolation theory, which I think it's good to understand when things work and when they don't work. And I think from the practitioner's point of view, it's good to know that now the more computational effort you're spending into your problem, if you have these methods that are asymptotically optimal, you're getting the benefit that the better solution you're going to acquire out of them. But at the same time, as Sertaç pointed out, there is no free lunch. We need to invest more computational effort in finding high-quality paths than finding just a feasible solution. Right? Every time that you throw a node, you have to connect to log-n neighbors. You have to figure out collision-free paths with multiple connections at every iteration of the algorithm. So what was the impact then in the community after this paper came out? What changed? Well, from one point of view, everything changed. It's a revolution in the field, right? For many of us, now there was an opportunity to actually try to understand, all of these other versions of the problem, perhaps, for where we can argue asymptotic optimality. There have been improved analysis models, for instance, Marco Pavone's group has done convergence rate analysis, which I think is very important. And also versions of these methods that perhaps have reduced computational requirements and they can achieve some weakened form of asymptotic optimality, perhaps asymptotic near optimality. And, there were many applications now that they switched from using just the feasible approaches to these asymptotically optimal planners because hopefully we can get, these better quality solutions. Now, Chris asked me also to be a little bit controversial. So from one point of view, you can also say what changed after this development? Well, not much. We're all kind of still doing, the same type of motion planning that we were doing before. There are many alternative approaches. I think there is still a quest for, the right motion planning approach that appropriately balances efficiency and high quality for real-world applications. There are efforts in heuristic search, there are efforts that, perhaps in the navigation potential functions, especially in the multi-robot literature. Over the last decade, from 2010 to 2020, there has been, renewed and recurrent interest in trajectory optimization approaches. And if you see some papers, and I'm picking here one paper that actually tries to bridge trajectory optimization with asymptotically optimal planners, you will see comments such as, sampling-based planners like RT star converge asymptotically to optimal solutions. However, they are kind of slow to converge to the optimal trajectory. You actually have to sample close to the vicinity of the true optimal solution. And, this keeps motivating, new work. And I think it is a promising direction of seeing, how we can have the global optimality guarantees that these methods provide, at the same time gain the practical benefits that may come from the solutions such as trajectory optimization. And of course, there is an 800-pound gorilla in the room these days. Her name is machine learning. And there's a lot of work as well in integrating sampling-based motion planning with machine learning. And this kind of work reminds quite a bit the work that was happening before the development of RT star and PRM star. We're trying again to develop better sampling strategies, better connection strategies, faster collision checking by using machine learning, but this time, more data-driven. There are frameworks like neural motion planning approaches that kind of replace the entire sampling-based pipeline with neural networks that are very actively explored. But I think one big challenge is that perhaps it's about time we get to have a paper like the one by Sertac and Emilio. Can we achieve a foundational understanding of how and when the integration of learning and robot planning works? Perhaps we can see that in an upcoming RSS paper. Thank you.
Okay, so I just wanted to say that I thought that this paper was remarkable in a number of ways, not just in the impact it's had on our field, but the journal version especially was remarkable because of its exceptional length. It was 76 pages, and yeah, I feel sorry for those reviewers. But really, one of the other sides of the coin that we haven't really seen, well, I guess we've discussed it from more of the sampling-based motion planning side of things, but I think there was a palpable realization that these sampling-based motion planners had problems with optimality. And we started also seeing around the same time folks working on trajectory optimization-based approaches, the CHOMP work by Chitta et al. There's some work by John Schulman on Trajopt. There's work by Murin Kobylarov on cross-entropy motion planning, where they're like, hey, we need to optimize paths. And so they kept reinventing sort of trajectory optimization, and then everyone from the sampling-based planning community was kind of poo-pooing that, well, these are local optimization methods, you have no guarantees, et cetera. And they had no answer for how to actually get high-quality paths. And this paper was the first one where we really felt like there is an answer. It also showed us that the right thing to look at if you're looking for both practical performance as well as guarantees is this idea of asymptotic optimality. You want to eventually approach the optimal path. You could look at, for example, these plots of time versus cost, and you want that to quickly approach the optimal path cost. And that gave us the right kind of frame for looking at performance of all these different planners, and essentially unified us to kind of realize the importance of this quantity of asymptotic optimality. One other thing I wanted to mention, I wanted to echo what Kostas said. I think we were also in a stage where there were hundreds of papers being published every year on different types of sampling strategies or connection strategies for sampling-based planners, and it seemed like we were kind of floundering. We had a lot of different, approaches and new methods coming out with new acronyms and so on. What does that sound like? Learning. We're in a stage where we needed some consolidation. We needed something to kind of unify our way of looking at the world, and I think this paper actually really did that. Hopefully, again, as Kostas said, we'll find something like that for learning and motion planning or learning in robotics more broadly. This paper had really sound theoretical guarantees. So there's a lot of you who are very excited about building methods, and so we see this kind of rapid fire kind of methods after methods after methods, new methods coming out. But when you have a more foundational paper that has something to say theoretically, and these papers are both practical but also extremely theoretical. Most of those 76 pages of that journal paper are proofs. Some of you don't like to work on proofs, but proofs are extremely important for our field. They're touchstones. If you prove something about a problem that people care about, it's a significant thing, much more significant than another method that your group can work on and nobody else can use it, and so on. So I encourage you all to think more theoretically about your work, and this is an inspiring piece of work for that. One final thing I'll say is that I wasn't aware of this this Overmars paper that had that comment about how adding more connections will lead to better quality paths. When I was a grad student in like 2007 or something like that, also working on sampling-based planning, I had this thought: well, what if you kept adding more connections to your roadmap? And 15 minutes later, it was like, yeah, you'd probably approach the optimal path. Yeah, it would be probably pretty expensive. And when this thing came out a few years later, man, I just kicked myself. I'm like, I should have, investigated this further, right? So yeah, I'm jealous. But they really did a great job on investigating this little, question that was kind of bothering people. Like they identified this question that was sort of bothersome. You can even see the history of it, right? Something is weird, right? So if you're a grad student here and you have a feeling that something is weird, push on it, because you're going to come up with something. And if that weirdness is, if you're feeling that weirdness, probably everybody else is too. And I guess I'll leave it at that and pass it on to Danny.
I have a problem. I'm the fourth speaker in this session, and I have to go again through the same history. But I want to do it from a somewhat more personal, subjective perspective. You know that the PRM paper was by Lydia Kawraki and Jean-Claude Latomme then at Stanford, and by Mark Overmars and Peter Schweska from Utrecht. I was then in the 90s at Latomme's group. Latomme was Chris's advisor. Later, Lydia was Costa's advisor. And you probably know their name, but Mark Overmars, that was already mentioned here, was a very important computational geometer. He was one of the founding founders of geometry. And while at Stanford, I visited him in Utrecht, and he was excited like a small child, showing me this trivial motion planning problem with 2 degrees of freedom, where he adds dots on the screen and connects them by line segments and solves the problem. And I understood that something is going on, and I refused to get excited. And I was wondering to myself, what happened to all those smart people? What is this silly game that they are all playing? Of course, this was juvenile arrogance. And slowly, it turned out that there is a new tool that can solve motion planning problems that were not solved before. Still very limited, typically simple problems, no guarantee whatsoever. You don't know if the program will stop after split second and give you a solution. It can run for 5 days. You don't get a solution, and you don't know whether there is a solution or not. Anyhow, there was something going on here with no proof, and then comes Steve Laval, and as he testifies, on his way back home from work, he dedicated 5 minutes to this problem and came up with RRT, the 5 minutes that bought him world fame. Again, something big happened, because many problems that were not solved by PRM were now solvable efficiently. But there was this problem that you could get horrible solutions. And I had a hobby with some of my students to produce bad solutions with RRT. You can take a problem, move a point in three-dimensional space among polygonal obstacles, and you easily get a path that is 150 times the shortest path as a solution from RRT, and without difficulty, with significant probability. So again, something was happening, very big thing was happening. Many problems were solvable, but things were missing. And I'm skipping hundreds, as Chris said, hundreds of planners and important contributions and hundreds of acronyms. In the mid-'80s, Steve Laval published a wonderful treatise, the book on motion planning. He summarized everything that you ever wanted to know about motion planning up till this time, but something was missing. Enter Sertac Karaman and Emilio Frazzoli, and really the motion planning world and the robotics world has changed forever. Suddenly, there was this tool that is well-founded, gives you a direction what to do in practice. You know, it was already mentioned that the star in RRT star is computationally very heavy. But at least if you are willing to invest the time, you are heading in the good, optimal direction. And of course, there is this beautiful connection that they made with the vast and deep literature on a random geometric graph. One cannot overestimate the contribution and the revolution that the paper that we are celebrating today made in the field. I do want to look ahead and say that something strange happened with the robotics community. We want practical solution, and you may know that in the 80s there were some seminal papers by Schwartz and Sharir on the piano movers problem, and John Kenny later came up with a more efficient solution to the general motion planning problem. And I jumped from that about 35, 40 years to the paper by Karaman and Frazzoli. And what happened in this, the robotics community substituted one asymptotic analysis with a different asymptotic analysis. In the 80s, it was the crucial parameter was the complexity of the robot and the environment. And in Karaman and Frazzoli, it's the number of samples. But asymptotic analysis can be misleading. It sweeps a lot of important practical factors under the rug. Now, some people may tell you that motion planning is a solved problem. I think this is a grave mistake. We can handle simple, often non-trivial cases. But there are many hard, relevant robot motion planning problems where we do not have a clue. We are completely in the dark there. And I want to appeal to the younger researcher in the audience for action. And my hope is that in the future, eventually, one of you will get the Test of Time Award for making substantive contribution to motion planning. Thank you.
Should we take a couple of
2 minutes or so? Yeah, 2 or 3.
So we have maybe a couple of minutes to take a couple of questions if somebody would like to step up to the mic.
Perhaps we should bring Sertac?
Yeah,
You don't necessarily have to have an idea for a Test of Time award-winning paper. Yeah, why don't you walk to the mic? Sertac, I hope you can hear us as well.
Yes, I hear you all.
Awesome. I will just ask a very simple question. So, what are the I don't know, what do you think the future directions are for task and motion planning? And what are the open challenges that you think they'll be interesting to look into nowadays? Yeah. Thank you.
And I guess if that's a question for me, I mean, I could list many. If you were thinking about just sampling-based motion planning on its own, I actually was going to refer to, but I did them later, is there's Kostas Bekris here has a really great survey paper. It's pretty, but there's some directions over there that I'd definitely take a look at. If you're thinking about motion planning broadly, I again agree with that, with Kostas on that. In particular, I think one of the things that we struggle with nowadays is how we utilize machine learning, or how we utilize data actually broadly. It doesn't have to be the kind of machine learning that we kind of quickly got used to today, like neural networks, lots of data, but it could be in very different ways that just whatever we couldn't do with models, we worked on that a lot, and this paper was completely on models. But how do we actually incorporate data? And I would say one of the biggest challenges there is maybe kind of, at least from my a little bit applied background outside of academia, I imagine Emilio would agree, is how do you actually take that and make sure you also guarantee safety? Just being safe in some ways is not enough. You also need to know that you're safe, which ends up being a very important challenge. I could list many, but maybe I'll stop here, and if any of the panelists would like to take, I could leave that to them.
Thank you. Maybe we'll take one or two more. So if the next person would like to step up.
Hey, I just wondered if you could comment on the impact of these ideas in industry. Full disclosure, I work for real time sometimes. Thanks.
Okay, that was that. I mean, I cannot see who's in the audience, but I think that was definitely So what I was kind of thinking is that I think that for at least what happened to how we perceive things is, I mean, a lot of the things that we found in the paper ended up being more like insights. And so we ended up taking those insights and utilizing them to build, what we thought would be efficient algorithms that would, for example, be useful in self-driving vehicles. I think we implemented in some ways bits and pieces of these algorithms, but the way at least I see it is that it ended up changing our thinking a little bit. It's not that we dropped completely, finding good sampling strategies, or dropped completely, repairing the tree in different ways, but we thought that there's some other, foundational things we can change in the algorithms and get to, solutions that we expect from these vehicles, but at the same time do it very efficient. And so in some ways, I think for me at the very least, it was a bit of an insight and change in thinking, as opposed to, okay, so we took this algorithm and put it there and boom, it works. And we've been very successful commercially. I don't think that exactly is what happened. But I do think that for me, at least, was very valuable in kind of changing our thinking.
Awesome. Please, go ahead.
Cool. Thank you. This is a really interesting discussion. I wanted to ask a little bit more historically. So a lot of you are talking about the context in which this paper could arise and make a big contribution, talking about the Urban Challenge team and also about a context of a lot of different papers. And I was wondering if you could reflect more specifically on what about the environment helps a contribution like this become possible, and also for now, are there things that we can learn from this process that we can bring into the current community?
Yeah, okay, so I guess, it's another question for me. So that's a good question, but, here is, I think, maybe what happened on our end, both for myself and Emilio. I think we had a solid preparation to do theoretical work, even before I'd say for me starting graduate school, and I think Emilio is no different. And I think we also had a passion for, really the application. I mean, we wanted to get our hands dirty, and maybe them together was a little bit better, so we could see things and try to improve. And I wouldn't also underestimate, our colleagues, as I said earlier, who really didn't take simple answers and kind of, waved hands and moved on. And they really kind of pushed us to really do things well. And maybe it was a bit of a combination in that way. But I would say that, I really appreciate, the panel and the audience for the award and their words. But to be very frank, as many of the people mentioned, I mean, ideas like these are, I think, were in people's minds ultimately. And I think if you go back and, maybe if you talk to people like who were mentioned here, Latombe or Overmars, maybe they would have even known about sort of this literature. But ultimately, there's a little bit of maybe kind of really going in there, going in depth, and actually kind of carrying it forward and trying to exploit all the little bits and pieces. Like as people say, sometimes idea is like the 5%, and there's the 95% of the work, and we kind of got a chance to maybe do that at that time.
All right, so I think we'll unfortunately have to stop here. I know there are a couple more questions. I'm sorry we can't take them. Once again, let's please give Surtash a hand and also thank our panelists.
Thank you so much.
All right, and this formally ends the session. Thank you very much.
Folks, if you are attending the lab tours, please meet our volunteers right outside the auditorium. So exit that way towards Broadway, and our volunteers will be there to guide you to the engineering school.
Does anybody know if the tour got back? Should we wait for them? If they're not back, I guess perhaps we should wait. There's something like 75 people there, so okay, we'll wait a few minutes.
Oh yeah, shall I? Okay.
All right, so I guess we should probably get started in the interest of time. The chair of the next session and our last session is Jens Kober.
Thanks. Apparently not everybody's back yet from the tour, so let's hope it's going to fill up a bit more. The first talk is going to be given by Will Mandel on action condition tactile prediction.
Maybe. Oh. Okay. Is it playing? Yeah. Okay. Hey everyone. I'm Willow, and this is my work on action condition tactile prediction with a case study on slip prediction. Okay. So tactile sensation is often applied in a reactive manner. For example, when dealing with object slippage, projects often generate binary slip signals from tactile data, classifying with a tool like random forest, and then when slip trend is detected, you increase the grip force on the object. And that works really nicely, but if we can perform tactile prediction over time horizons, it will enable proactive control within the same scenes. giving us a greater range of control techniques and potential solutions that we can apply. In the case of slippage control, that might mean not increasing the grip force because the object's delicate or we're already at max grip force, and instead doing more appropriate control with joint space trajectories or adjusting the grasp position on the object. And although some researchers attempted to perform tactile prediction before, these projects were very application focused and they didn't provide us with any insight into the tactile prediction problem itself, only in how to use it afterwards. So in our work, we did a comparison study between different unsupervised learning models applied to pick and move motions, and we further explored prediction models within the context of a slippage prediction application, where we try to work out if and when slippage will occur during a pick and move task. So on the left-hand side, or my right-hand side, is an example of the pick and move trials that we were performing in our data collection. And on the left-hand side is the tactile frames during this pick and move. And as you can see, it consists of just lifting up the object and moving it around and creating some slippage. And we created these motions using pseudo-random teleoperated motions from humans, where we basically said, can you create as much slippage as possible? And it occurred in around 10% of the frames in our data set. So we used a low-resolution magnetic-based tactile sensor called the Zeller U-Skin, which takes shear X, shear Y, and a normal Z force. We also stored in our data set the robot states, so we could actually condition our model. And finally, to test, I'm not sure what's going on there. And finally, to test slip prediction, we also attached the Aruco markers to the side and top of the object, which allowed us to classify when slippage was happening by thresholding on the yaw values. The data set in total was 52 trials for training and then 22 trials of unseen objects for testing. So to compare and contrast our possible key features that we might apply to tactile prediction, we analyzed the prediction performance on the state-of-the-art tactile prediction models like Pixel MotionNet, as well as some simple benchmarks like MLPs, and some video prediction algorithms like CDNA and SVG, as well as developing our own models in the setting, which we called action-conditioned tactile predictor, and a video version of the same one, action-conditioned tactile video predictor. So within the comparison study, we showed that our model ACT-VP, the video predictor, worked best with respect to like standard performance measures, but what we found was that when we did qualitative observations of the plots, we found that their indications weren't very realistic, and we found that our linear-based models, ACTP, performed much better predictions that were both smoother and predicting tactile changes ahead of time, like you can see on the bottom here. We also found that, I mean, naturally, at the beginning of the system, we're not able to predict these changes in tactile behavior. That's when the grasping is happening. So we don't provide any like visual information about our object. So the system's never going to be able to predict the picking. It's just the motion afterwards. So when it comes to slippage, to generate the slip predictions, we use random forests on the predicted horizons of our tactile systems, producing slip classification at just t plus 10. The performance metric we used was a combination of both the slip percentages that were picked up in the data set, but also how close the slip instances were to the ground truth. On the right here is a nice example where we see the tactile predictions and then the classifications to slip during a 15-second pick and move trial. Yeah, finally, we found some interesting features. Like, for example, we found that the video-based prediction networks actually had a negative impact on tactile prediction, and there was a variety of other features that we found counterintuitively weren't helping. So in summary, what we found was that our comparison technique showed that our model was the best performing model in the data sets. We further compared this on a tactile prediction, slip prediction task, and one of the key limitations of our work was that we only tested on flat surfaced objects, so we thought for future work we're going to try to do predictions with non-flat surfaced objects. Thank you very much.
Next up, we have Shupeng Xu, who is going to tell us more about sample-efficient grasp learning using equivariant models.
Thank you. Hello, everybody. My name is Shupeng Zhu from Northeastern University. Today, I'm glad to present our work, sample-efficient grasp learning using equivariant models. It's joint work with Dian Wang, Andre Bizarre, Guang Su, Robin Waters, and Robert Platt. So grasp detection is an important trend in robotic grasping, which utilizes machine learning to train a neural network Q that is able to infer the grasp pose and the position A from an image observation S. So the current grasp detection method is able to learn a good grasp function and generalize to novel objects. However, they suffer from low sample efficiency, which typically requires millions of grasp samples or hundreds of robot hours. Moreover, some of the methods use simulated data suffer from the scintillation gap. That was due to the simulation dynamic mismatches the real-world dynamic. So, for our method not only able to learn a good grasp function and have the generalization ability, but also boosts the sample efficiency by orders of magnitude, so that we only require hundreds of grasp samples or equivalently 1.5 robot hours. Such high sample efficiency enabled us to train from scratch on a physical robot, therefore overcome the scintillation gap or potentially the uniqueness of the robot hardware. So the core discovery is that we found the grasp function is equivariant. Let's take image S for an example. Through grasp function F, we obtain a grasp pose A. Now, if I randomly translate or rotate the image S by G, the grasp pose will be translated and rotated correspondingly. This indicates that the grasp function is equivariant to translation and rotation, as denoted by equation 1. So what we do is we enforcing the equivariance using equivariant neural network. Therefore, for network Q, it inherits such equivariance property. So what is equivariant network? It's a network have a set of the convolutional filter that not only translates, but also rotates. Therefore, once the network learns a set of the convolutional filters for image S, it automatically generalizes to any translated or rotated image GS, as shown in this slide. So once our grasp function Q learns the grasp pose in this image state, it generalizes to any translated and rotated images. Notice that we only use the depth image, for it is sufficient to learn a good grasp function. And besides this, we also use the method called ASR to reduce the complexity of evaluating the entire action space. So we have a two-stage inference. First, we use Q1 network to evaluate the translational actions and select the translational action. Second, we take an image corp centered at that selected action and feed it into the Q2 network. Now, the Q2 network evaluates the rotational actions. So for Q1 network, we choose default equivariance, and for the Q2 network, we choose C16 equivariance. So as we said, we train our method completely from scratch on the physical robot. The training set includes 15 objects. Testing set includes novel 15 objects. The left video shows the training process and the testing process. As you can see, at the beginning of the training, the robot just performed random grasps in the tray. It's about 20% success rate. And after a while, roughly an hour of the training, it achieved 80% success rate. And at the end of the training is about 90 minutes. We tested it on the novel cluttered objects, and it achieved 95% success rate. The right figure shows the learning curve. The x-axis is number of grasps ranging from 0 to 600, and the y-axis is the success rate. Our method, denoted by color blue, reaches much higher sample efficiency. Yeah, feel free to ask any questions in our poster session. And our code is open sourced. That's it. Thank you.
For the third talk, we're going back to tactile sensing, presented by Joe Huang on understanding dynamic tactile sensing for liquid property estimation.
Hello, I'm Hongrui Huang. For robots to operate in our households, they need to be able to perceive common objects. One common class of object is liquid, such as sauces, drinks, detergents, and so on. In this video, by shaking the container, human can use tactile sensing to quickly answer questions like how much liquid is left, how viscous the liquid is. We want to enable robots for such an ability. When we interact with a bottle, different liquids will have different movements, which is caused by the liquid properties. In this work, by interacting with the container, we want the robot to infer liquid volume and viscosity in the container using only tactile sensing. A common approach is to learn to predict liquid properties using the tactile patterns in a purely data-driven way. However, these data-driven approaches often require a lot of data and suffers from low accuracy. Another approach is to build a physics-based model by analyzing the fluid dynamics of the liquid content. However, their model is limited to cylinder containers with precisely known dimensions. Our approach complements the data-driven and physics-based approaches by modeling the principal liquid dynamics using simple physics and learning the complex unmodeled dynamics in a data-driven way. We call it a physics-inspired approach. When a resting container is perturbed, the surface of its liquid content will oscillate and gradually decays away. When analyzing the system energy using the principle of working energy, we can see that the system oscillates because of the energy exchange between the kinetic and potential energy. The oscillation decays because the liquid's viscous force acts like friction and gradually dissipates the system's total energy. We therefore derive that the system is a second-order system. The takeaway of this model is that the decay rate is governed by the liquid viscosity, and the oscillation frequency is governed by the liquid surface height. In our method, the gripper first grasps the bottle with 2 gel-side tactile sensors and make an impulse movement. We collect the dynamic tactile signal in a free oscillation period. We track the markers of gel-side, extract the tactile data, and fit it with a damped oscillation signal. As the physics-inspired model suggested, the decay rate lambda and the oscillation frequency omega of this damping signal are highly relevant to the liquid viscosity and liquid surface height. We learn this relation in a data-driven way because it is affected by the complex shape of the container and the unmodeled dynamics. We take multiple experiments to prove our method. First, we'll try to classify 3 common liquids: water, oil, and detergent. Their viscosities are different, leading to different oscillation decay rate lambda, which can be perfectly extracted by our method. We achieve 100% classification accuracy for water, oil, and detergent, even without fixing their weight and amount. In addition, the model can be trained with only 24 data points, showing that our method is super data efficient. Secondly, we target a liquid with smaller differences, the sugar water with different concentration and height. We train a Gaussian process regression model using lambda and omega as input and regress the sugar concentration. We achieve a concentration regression mean average error of 15.3% and log viscosity prediction MAE of 0.16. It shows that our method can estimate the concentration of sugar solutions by only tactile sensing. We use the same data set and method to regress on the liquid height. We achieve a high regression MAE of 0.56 millimeter, which is near the limit of the ruler's precision. Additionally, the same model can also be used to estimate viscosity and height of unseen liquids such as marine. We also show our method can be generalized to different containers, such as a large cuboid container on the left and the cylinder bottle on the right. In addition, the model can be transformed between different containers. Based on the trained model of the groove cuboid container and some limited amount of fine-tuned data on a new cuboid container in a different size, we can fit a model for a new container. With only 15 fine-tuned data, the tuned model can predict well with the concentration prediction MAE of 19.3%. To conclude our work, we propose a physics-inspired model of the liquid container system for dynamic tactile sensing. Based on this, we achieve liquid viscosity and liquid height estimation. We also show our method can be generalized to different liquids and different containers well. Thank you for watching, and I'll see you at poster 17.
The final presentation in the first block before the Q&A is going to be given by Griffin Tabor on adaptive manipulation of conductive non-magnetic objects by a continuous model of magnetically induced force and torque.
It's a bit of a mouthful.
Yes.
Hi, my name is Griffin Tabor, and I'm here to talk about our recent paper, Adaptive Manipulation of Conductive Non-Magnetic Objects via Continuous Model of Magnetically Induced Force and Torque. Our research builds on using eddy currents, enabling us to produce force and torque on conductive objects, which, while not unknown, manipulation with these effects is relatively unexplored. In a nutshell, it works by moving a magnetic source and a conductive object relative to each other. This produces current on the conductive object, creating a small magnetic field that then interacts with the original magnetic field. Specifically, we think this type of manipulation will be especially effective at cleaning up the thousands of pieces of space debris that we have left in space over the last few decades. These pieces are largely aluminum and titanium and tumbling in haphazard orbits. Classical techniques of manipulation are ill-suited because the object motion would be dangerous to a physical manipulator. We recently published work where we categorized the force and torque produced when you rotate a magnetic dipole source near a conductive object in 3 different configurations. With respect to the vector between the magnet and the object, these configurations are parallel and anti-parallel, shown as the green and blue arrows, or orthogonal, shown as any of the red arrows. We fit this new novel model and put it into wrenches in the world frame to get these 3 actions. The model shown previously, however, is not invertible. To use it in a controller, we need a way to map desired wrenches to control actions. This turns into an optimization problem across each magnet and each action, selecting optimal continuous values subject to bound constraints. Here we show 6 magnets in simulation manipulating a sphere in 6DOF. Recreating these experiments with physical experiments is not feasible. We wanted a frictionless zero-gravity simulation. Instead, we simulate zero gravity on the surface of water and physically demonstrated manipulation in 3DOF. For this work, we try to fill in the gap in our previous model, supporting arbitrary axis of rotation. We define theta to be the angle between the axis of rotation and the vector pointing towards the object. In this framework, the old model was theta equals 0, 90, and 180 degrees. We collected data at different values of theta using similar methodology to previous work, a combination of benchtop tests and FEA-based simulation. Looking at the data, we see a clear sinusoidal trend, with the largest in the rho dimension, which is the axis pointing towards the object. We take the value of the old model at its 0, 90, and 180 degree positions and use simple trigonometric functions to interpolate them. Given a vector rho between object and magnet and a dipole rotation axis omega, we can rework our model from spherical coordinates into some end effector frame. To go with the new model, we need a new updated control optimization. Previously, we independently searched over each magnet and each mode. The new continuous model allows us to search over an entire magnet's control space, in this case psi and z, to select the unit vector omega, as well as dipole strength. Up until this point, we have focused on modeling known spherical objects and manipulating them. But the goal is to move towards real arbitrary objects. Given data from a manipulation experiment, we can perform system identification to identify the object properties that best explain the observed motion. We use the same force-torque model we use in our control optimization to create a simple least squares optimization problem. Additionally, we solve the same problem online. Our adaptive controller, building a local dynamics model, enables us to fit our model of spherical objects onto objects that could never be globally modeled as a sphere, and use our adaptive control on spheres and non-spheres alike. It is also interesting to note that all 4 objects here were initialized the same as a small copper sphere, and the PID gains and PID controllers are identical for all of them. The difference between them is captured in the model adjusting the current estimated object size. shown here as ghost objects. So in conclusion, we expanded the modeled region and removed the discrete components. We introduced adaptive control to allow manipulation of unknown spheres. And we demonstrated the first non-spherical object manipulation with eddy currents. We're at poster 18. Happy to answer any questions.
Yeah, I can stay up here for the Q&A. Let me just go grab the mic. Any questions from the audience or online? If not, then I'll just kick it off with a question from my side. So for Will, first talk. I was wondering how specific your method is to the tactile sensor you're using, and if that would make a big difference if you swap it out to an optical one, for instance.
Yeah, I think it. Hello, hello. Yeah, I think it would make a big difference. I think the low resolution of our tactile sensor helps us in our scenario because we're using flat objects. So it's a low resolution problem. But as you start to test on more varied objects, like I think of like Lego brick style nodules on the end of the object, I think you'd have to use a more high resolution sensor like an optical tactile sensor.
Great, good. Still no questions from the audience. Good, then I'll just continue with a few more. For the equivariant models, so I mean the obvious question is, why is it better to embed that in the network structure itself rather than just doing a whole lot of data augmentation by rotating the images and shifting them?
That's a good question. Actually, from the baseline comparison, all of the baselines have selected from the extensive different data augmentation parameters, but still our method outperform. A simple question for it is, the data augmentation only can guarantee the equivariance in the data you have experienced, but it not guarantee for the unexperienced observation or new objects. But the equivariance model can guarantee such equivariance in even unseen objects.
Okay, thanks a lot. Finally.
Yes, I had a question for the grasping and determining viscosity and fluid levels. And so I'm curious because the videos you showed sort of had it grasping in the same position, the bottle's in the same position. So if I grasp the bottle upright, would you have to sort of train a new model for that sort of orientation? And I guess, are there ways to maybe sort of extract like more fundamental information, so any way I grasp a bottle, I would still be able to figure out?
That's a good question. So first of all, like if you grasp it upright, like the oscillation is not like obvious enough for the tactile sensor to really grasp that, to really capture that data. So that's why we grasp on the horizontal direction. And technically, like we didn't. Every time when we put the bottle in between the fingers, like they're in slightly different locations, so we're never like trying to make it exactly the same position when we're doing our experiments. So like, but it still have to be around the center of mass, otherwise it might slip away. So it's just like some constraint that like inherently we made.
On this side, please.
Yeah. I have a question for the last talk. Really interesting talk. It's a really interesting problem. It's going to be a really important thing to address. How do you feel like the magnitude of the forces that you're using for the manipulation relate to the sort of ambient magnitude of dynamic forces happening in the magnetic realm in that region of the Kessler belt?
Yeah, so the easy answer is that the force is actually decaying so much with distance, no one else's effects are going to dominate the system. So we would be the largest magnetic field relative from the point of an object's perspective. There is questions of the amount of force we can produce that are important, which is not very much. The video is at 20x speed. These experiments are 40 minutes to draw a square in our tub of water. But the idea is that if an object is spinning haphazardly, there isn't really an alternative of how you grab it. So,
thank you.
Good, and then last question.
Yeah, I have a question for the third paper. Really cool work. I'm wondering, like, what's your intuition on extending that method to other type of tasks? For example, rigid objects, or the similar methodology applied to other kind of tasks?
So that's a good question. So I think the main takeaway of my project, our approach, is that we divide the approach into a physics-based and a data-driven. So it's a combination of both. So I think one thing that I really want to deliver is the message that in order to do that dynamic tactile sensing, it will be a good idea to kind of understand what you're trying to estimate. And it shows in our approach, for this specific task, if you understand that, then you can actually do pretty well, much better than just simple data-driven or simple physics-based. So you kind of need a thing from both worlds, because tactile sensing isn't that repeatable, and you need to know what you're trying to know. That's what my belief is. So hopefully that is but specifically this model, can it generalize to solid content estimation? Yeah, probably not exactly this model, but you can build another model, and we are also trying to do that in our group.
Got it. Thanks a lot.
No problem.
Then let's give all the speakers another big round of applause. And we can start the countdown for the last 4 presentations of the conference. The first of those is going to be given by Ed Bray on distributed optimization and deconstruction of bridges by self-assembling robots.
Hello, so my name is Ed. I'm from the University of Sheffield, and this is work that I did with my supervisor, Roderick Gross. So we consider swarms of robots, which are large groups of robots working together to accomplish one task. These tasks tend to be tasks which cover a large area, so these robots can spread out, or ones which require redundancy. So if a couple of robots break, the whole task can still be achieved. Typically, these robots are quite small because they have to be quite cheap to manufacture a lot of them, which has a few advantages, like you can imagine they can squeeze through small gaps, but other obstacles are much harder to overcome. This work focuses on how they can overcome, how they can cross gaps in the terrain through self-assembly, inspired by ants, as shown on the left, and sort of encouraged by previous work in this area. But we take a different approach to the one seen there. So we consider a 2D grid of agents who build a bridge between these two vertical fixed support surfaces. In work published last year, we focused on part 1 of this problem, which was building a cantilever. So incrementally building the structure in a force-aware way so that it won't collapse. We use this as a starting point for the work in this conference, which focuses on 2 novel problems. So from here, agents can become active, as shown there, and they communicate with the agent above, which tells them the moment and the axial force in its links. We calculate criticalness from this, which is how close that link is to failure. The robot moves around the structure like this, and it can also pass through into the 3rd dimension to travel between the top and bottom surfaces. Using this framework, we consider 2 novel problems. So we first consider, once the other side of the bridge of the void is reached, we can maybe lose some robots and they can do something else on the other side. We call this optimization. So it's reducing the number of robots in the structure while maintaining stability. We also then consider how you could deconstruct this structure, again, while making sure it doesn't collapse. We do this by first extending and building a strong structure and then deconstructing column-wise. We'll look at this optimization problem first. So there's only time for a really quick overview here. But basically, agents switch between a few modes. So they start off as placed, and they become active in the releasing mode based on how much force is in their links. At this point, they move underneath the structure and gather data as they go. And eventually, if they believe the structure is stable, they will leave it. But if they believe the structure is unstable, they'll try and place somewhere depending on the force information they've reached. So they try and place somewhere probabilistically near an area of high force. If 2 agents are traveling in opposite directions and can counter each other, they just swap information and become one another because it's a homogeneous group of agents. This is best shown with a video, which we have here. So on the left, you'll see robots moving around, and the links between them are colored by the criticalness, like the force in the links. And on the right, there's an overview of the moment and the force throughout the structure. So this agent has become active, and it will first travel to the left, and here it's swapping with another one that's trying to go to the right. So eventually, one of these agents will reach the right-hand side, and this agent has decided that the structure is stable and it can leave happily without causing the structure to collapse. This continues until eventually one of them decides the structure is unstable, and you see it places there to try and reinforce it. So we have this trade-off of agents placing and moving around. If an agent releases but makes the links around it critical, it places back where it was. And this continues until 50 steps pass without any change. And then we've reduced to 26 agents there from about 100. Now we'll talk about the second problem, which is deconstruction. So it's similar to before, but we have one new mode called force releasing, so agents can tell each other to release if they need to. Gathering agents enter the simulation above the right-hand side, as shown there, or they can release as before. And they place, depending on whether they believe the equivalent unsupported cantilever is stable, which is the region shown there, which basically means like if the agent left of that was released, would that cantilever be stable? And this, we calculate this by augmenting the force information using some elastic beam theory from civil engineering to calculate this. Again, this is best shown with a video, which we'll play in a second. So agents add themselves from the right-hand side, as shown, and this one will move around. When it gets here, it will release the one on the left of it because it believes that equivalent unsupported cantilever is stable. So now you can see agent 23 will release itself, and then continue like this. And agents can release as before on the left-hand side there. So again, agents are like adding themselves and also reconfiguring from the left to build a strong structure. And eventually, one of the agents decides that it's safe to release that agent 0, and then the structure would deconstruct column-wise after that. Yeah. Cool, so that's all we really have time for in this presentation. There's a lot more in the paper, including some calculation of optimal bridges and some conflict resolution, and also like an analysis of a maximum momentum force. In future, we hope to implement this on real robots. I know people are crying out for systems in this paper, in this conference, so I've got a system here, which I'll be showing off at the poster session later on. Thank you.
The next talk is by Lasse Peters on learning mixed strategies in strategy games.
Hi, my name is Lasse Peters, and I would like to present to you our work on learning mixed strategies in trajectory games. Dynamic game theory, which is the focus of this work, studies the strategic interaction of multiple players with individual objectives over time. As a running example throughout this work, we consider the game of tag, for which you can see a real-world example here. This kind of problem is particularly interesting since competitive play in this scenario requires players to maintain a level of unpredictability. To highlight this challenge, we consider a simplified model of the tag game played between a point mass pursuer and evader with positions constrained to a polygonal region. This problem can be cast as a coupled optimization problem in which the objective of the first player, the pursuer, is to minimize the distance to their opponent while the evader seeks to do the opposite. A key challenge with this formulation, however, is that it only considers deterministic behavior, which may be exploited by a competitive opponent. For example, consider the scenario shown on the right. If here the red pursuer can predict that a rational evader would go to the top, they could chase them down into that corner. And to address that challenge, the goal of this work is to compute strategically randomized, so-called mixed strategy solutions to trajectory games. To this end, we propose a lifted formulation of trajectory games in which players now optimize their expected cost by choosing both the weights and the support of a categorical distribution over multiple trajectory candidates. And at runtime, players sample from this optimized distribution to minimize their expected cost. You can see an example of such a lifted strategy on the right, where now the evader randomizes between either going left or going right, and thereby also forces the pursuer to consider multiple options. While this formulation does indeed admit non-exploitable solutions, it unfortunately also introduces a computational challenge since it drastically increases the problem size. And therefore, the second contribution is that we propose a novel computational method to solve these lift games efficiently. The key idea behind our approach is that for given trajectory candidates of all players, we can rapidly compute the equilibrium mixing weights Q by first evaluating each player's cost for all possible trajectory combinations and then solving a bimatrix game over the resulting cost matrices A and B. For the resulting equilibrium mixing weights and cost matrices, we can then directly compute the expected cost for each player. And the key insight underpinning our method is that this entire computation is differentiable. In particular, we show that a bimatrix game can be differentiated efficiently. We use this gradient information to train a trajectory generator for each player, which predicts competitive trajectory candidates for given game configurations. And by embedding a differentiable trajectory optimization layer in each of these generators, we further ensure that the generated candidate plans remain feasible throughout the learning procedure. The resulting structured learning policy admits inference and gradient computation within milliseconds on a standard laptop. To demonstrate the effectiveness of this approach, here we show our method learning from scratch in receding horizon self-play for the tag game. Within only 2 minutes of training, we are able to learn highly competitive mixed strategies for this problem, for both players. So we perform a range of evaluations of this method, for which I would like to highlight the following main results. First, when comparing against the baseline, which uses sampling to discretize the game, we find that such an approach requires many samples to match the performance of our learning-based method. Further, in decentralized head-to-head competition, we find that lifting provides a competitive advantage over non-lifted formulations of the tag game. And finally, we also obtained preliminary results which demonstrate that our method scales even to many player general sum settings, like the 10-player collision avoidance scenario shown on the right. So to summarize, the main takeaway of our work is that we enable the efficient computation of mixed strategies for competitive play by combining differentiable games with trajectory optimization in a structured learning framework. For more details, please come see us at the poster. We have poster 20, or visit the project website below. Thank you.
Next, we'll hear from Marcus Pereira about decentralized safe multi-agent stochastic optimal control.
Hi, everyone. My name is Marcus Pereira, and I'm going to be presenting a new framework for safe and decentralized multi-agent control. Suppose we have 8 agents starting on a circle, an obstacle at the center, and the goal is to swap positions with the diametrically opposite agent like so. Now, if more than 2 agents simultaneously try this, it could lead to unsafe behavior. And therefore, the agents must learn to perform this task in a coordinated fashion, which in turn requires safe exploration. This is an example of safe behavior, but it requires an agent to be safe with respect to all the other agents, and for all agents to be safe with respect to the obstacle. We refer to this as the centralized approach, in which the agents are in consensus by default, but it does not allow reducing constraints or parallelization. So instead of trying to be safe with respect to all agents, let us only consider safety with respect to the most immediate neighbors. This allows for a drastic reduction in the number of constraints. Now notice that the pink agent actually belongs to 3 different neighborhoods, and that leads to a coupling of decision variables across the neighborhoods. To decouple them, we introduce copy variables, which are the ego agent's opinions on what its neighbor should do. Decoupling the neighborhood problems now allows for parallelization, but this comes at a cost. For instance, we could have agent orange's opinion, pink's opinion, and green's opinion on what agent pink should do. Now, in order to stay safe, they must agree on a mutually safe action. So the benefits of decentralization are reduction in the number of constraints, parallelization, at the cost of having to establish consensus. Now, formally, we aim to minimize this expected cost, which consists of a terminal cost term and a running cost term over a fixed time horizon, capital T, which is subject to the stochastic control affine dynamics of the system and a collection of user-defined safety constraints. This is a stochastic optimal control problem, and it is well known that it leads to the Hamilton-Jacobi-Bellman PDE, whose solution yields the value function. Now, solving this PDE directly is known to suffer from the curse of dimensionality, and we therefore adopt a recently developed scalable approach that uses FBSDs, where the forward SD is simply the dynamics going forward in time, and the BSD is governing the value function going backward in time. Now notice that the terminal cost is simply the terminal condition, and the running cost is the drift term of the backward SD. The safe and optimal control is obtained by solving the following constraint QP, where safety is ensured using stochastic control barrier functions. Now, backpropagating these BSDs are notoriously difficult, and therefore this deep FBSD architecture that we adopt parameterizes the unknown value function at the initial time with trainable weights. An LSTM network predicts the gradient of the value function fed to a safety layer, which computes a safe control to forward propagate the system. And this is also used to forward propagate the value function. Now, we repeat this at every time step, and this is the unrolled compute graph. Finally, a loss function that compares the true and predicted terminal value is used to train the network. Now the safety layer, one way to implement it is to solve the local neighborhood QPs in parallel in an inner loop until convergence, and then use consensus ADMM in the outer loop to solve for the consensus problem. But instead of this nested structure, we propose merging both the loops and solving both the problems in the same ADMM cycle. For this, we adopt the OSQP solver. The advantage is that each step is much cheaper and the overall algorithm is much faster. So presenting some of our results, the first task is along the same lines as the motivating example that we saw earlier. On the left-hand side, we see a single batch instance out of a batch of 64 instances. The goal there is to highlight that we ensure safety throughout the entire training process. And on the right-hand side, the agents are shown as point masses to show a distribution over the batches. Now notice that as iterations progress, the agents stop drifting away from the initial circle and a coordinated turning maneuver begins to emerge. On the right-hand side, we see that the same policy is able to control an ensemble of trajectories, showing robustness to noise and completion of the task on average. Next, we consider an unsymmetrical version of the same task. In spite of an unsymmetrical distribution of the 3 obstacles, the coordinated turning maneuver is successfully learned. In this task, there's a moving obstacle that the agents have to avoid going from the bottom to the top. The moving obstacle cannot be controlled and is an example of an uncooperative agent. In spite of this, the agents learn to both dodge the moving obstacle and learn the coordinated swapping maneuver. Here we see the final performance of a task where agents are able to squeeze through a bottleneck and get into a desired formation on the other side. And this is an application of a framework to a large-scale formation task. So in conclusion, decentralization helps in drastic reduction in the number of constraints, so much so that for large problems, the centralized versions of those problems don't even fit on a single GPU and are very slow. Thank you so much for your attention. Please stop by our poster.
And the very final talk of this conference is going to be virtual by Lillian Clark on prop EML.
Hello, my name is Lily Clark, and today I'll be presenting our work on radio propagation environment modeling and learning for communication-aware multi-robot exploration. Connectivity is a key component of multi-robot exploration, especially in harsh remote environments where data needs to be transferred to a human operator. For example, our experiments consider 3-wheeled robots, 3-legged robots, 1 base station radio, up to 13 static relay radios, and about 1 hour of exploration covering hundreds of meters. Predicting signal strength of a point-to-point link, for example, from a robot to another robot, to the base station, or to a relay radio, is useful for communication-aware decision-making by the robot. Extending this prediction to build signal strength maps is useful for operator situational awareness and strategic planning. Radio signal propagation is a multi-scale process. First-order models are a linear function of the log distance between the transmitter and receiver, which captures the attenuation due to free space. Second-order models consider shadowing or slow fading, which captures the attenuation due to obstacles. Third-order models consider multipath components or fast fading, which captures reflected and diffracted signals. For static transmitters, especially given a known map of the environment, data-driven methods can be used to fit accurate spatial models of signal strength prediction, and this is shown in prior work. For mobile robots operating in unknown environments, we investigate how the robot's onboard LiDAR, which is used to create partial maps, can inform signal strength prediction. The first contribution of this work is concerned with modeling the propagation environment between a transmitter and receiver, which depends on the geometries of the physical environment and the signal's characteristics, including the transmit power and frequency. From these, our model outputs salient features for propagation modeling. Beyond distance, these include whether there is line of sight, how much of the line of sight path is through occupied space or obstacles, and whether copies of the signal reflected off the ground or diffracted around a nearby object will cause constructive or destructive interference. So in a way, Prop M acts as an encoding layer between raw sensor data, which is these sparse 3D point clouds on the left, and a few key numbers for signal strength prediction on the right. To do this, Prop M internally builds and maintains a 3D occupancy grid used for ray tracing. The second contribution of this work is a thorough comparison of learned models, which use these features to accurately predict received signal strength. On the left, we show a snapshot of the performance of conventional models of signal propagation from the literature. True measurements are shown in blue. Overall, these achieve average errors between 6.5 and 12 dB. On the right, we introduce 5 fully connected neural networks, each which take a subset of the features encoded by Prop N and minimize the L2 loss between the predicted and measured attenuation. We observe that these models are better able to capture the data, and the richest of them, which we call NN-all, achieves an average error of only 3.73 dB. Given our interest in exploration, we then test these learned models in a new environment. Note that fitting the simpler models results in interpretable parameters. So we can immediately observe that the test environment is very different, with narrower corridors and more severe attenuation from obstacles. This demonstrates the need to update our learned models online by retraining periodically, while starting with the model trained offline prevents overfitting to the first few minutes of data. Relative to the baseline trained offline, our best performing neural network cuts the mean absolute error in half over the course of 1 hour of exploration with 6 robots. Additional results and discussion are included in the paper. To summarize, our approach uses 3 point clouds from the robot's onboard LiDAR to model how the environment will affect radio propagation, combines conventional signal propagation modeling and machine learning for accurate prediction, and updates online to adapt to new environments, which can even provide insight on the qualities of the environment itself. This inference is an interesting direction for future study. Again, my name is Lily. If you have any questions, feel free to get in touch. Thank you.
Is Lily online? Do we have any questions? We're trying to get Lily on the screen as well, so let's hope that works. Okay, then let me, oh, there we go.
Okay, cool. I have a question for the trajectory games paper. Did you guys find either the pursuer or the person fleeing, if any of them had any like dominant strategies at all?
Sorry, can you repeat that? Sorry.
Yeah, of course. Were there any dominant strategies for the pursuer or for the person being pursued?
So, like, you would very typically see that the evader, for the evader, it's very important to like randomize to like go either left or right. And you would very often see that if you have like a fast maneuver of like evading, you would sort of threaten the pursuer with maybe like decelerating and hiding in a corner. So that's like a very typical thing that we would see. Yeah. I'm not sure whether that answers your question.
Cool. Yeah, we can talk more in the post session. Thank you.
I can't really see if there's anybody. Oh, there's somebody upstairs, I think. Yes.
Hello. Hopefully people can hear me. I had a question for Lillian about the radio frequency propagation work. I think this may be less relevant in the cave environment you were working in, but it seems like in many cases there are sort of non-geometric material properties that might be important for radio frequency path prediction. So like a drywall wall might be different than a brick wall in a way that's not purely a property of its geometry. Is that something that you think your method could sort of be extended to handle, or is that something you think would be relevant?
Yeah, that's a really good question. For our method, where it stands now, it's sort of taking an average case of the environment because we're updating those specific parameters the same way. But you could think of an extension where you also pass in like certain other features like just XYZ coordinates, and then maybe if you had more data with, you could train such that you are learning not just for this much obstacle density, I expect this much attenuation, but like for this much obstacle density, which happens to be in this part of the environment, I'm seeing different patterns there. But that is a really hard thing to measure because the sensors that we have on board were not giving us any information about how sort of opaque to RF signals the different obstacles were. So another thing you could do would be to have different sensors and try to use those measurements.
That makes a lot of sense. Thank you very much.
Okay, second question from up there.
This is for the bridging paper. So I wanted to know what role does the synchronization or of the sort of like the tensile interactions between the agents play in the success of the whole scheme? Like if they were all making decisions asynchronously, would the scheme also hold up?
Yeah, so at the moment they are, as you say, making decisions all at the same time. It's like a synchronous process. I would imagine that it wouldn't make too much difference if it was asynchronous, as long as the communication was like reliable between agents. They only need to kind of know vaguely where they are on the structure in order to operate properly, I think.
Okay, thank you.
Hi, Lily. Great talk. So during your talk, you focused mostly on like evaluating how well you can predict signal strength. And I wanted to know how much you've thought about like how that relates to tasks and like task performance, or what tasks can benefit most from better communication models?
Yeah, that's another good question. We mostly were looking at this for specific applications in which you want to, the robot's trying to make decisions about where to return to in the environment where they would have good signal strength. So like SNR, like raw SNR was the only metric that we were really interested in, and that was the main application that we considered. If you wanted to get sort of more broader system level metrics, it would be good to look at things like how much data capacity was, like how much data actually flowed over those links, latency, like there are other things that we could consider, but that's what we focused on for this work.
Thanks.
Okay, and then the very final question.
Just to follow up to the last question for the bridging paper, do you feel like your model could be extended to where a situation where you don't have communication between all of the agents or where you have lossy communication between the agents? For the bridging paper, for the bridging
Sorry,
agents.
I thought you were following up to that.
No,
Can you repeat the question, sorry?
Yeah, do you feel like your method, you said they needed to have good communication. Do you feel like it could be extended to a situation where you have lossy communication between the agents or where you don't have complete information from all of the agents involved?
Yeah, so there is quite a lot of communication, but it's all local in this case. So I would, again, we've not tried it, but I would suspect if one or two of the communications are wrong, like if an agent miscommunicates its force, I think the algorithm would still work because it's mostly probabilistic based. So agents don't go to like the exact best place. They like calculate a probability distribution of where they could go. So maybe if they go to like the third best one, it's still fine.
Cool, thank you very much.
Yeah.
Good, then let's thank the speakers one more time.
All right, so that is the end of our main paper talks. We now have our last poster session for the next hour and a half, so please come back here at 4:30 for the award ceremony, acknowledgements, and then what's really exciting is the RSS Town Hall where we get to hear from you and have a great discussion. So enjoy the coffee break and poster session for now. 4:30, be back. Make sure to either sit near the aisles or near the front so we can call you up. You don't have to stumble over people. Thanks. We'll start in a few minutes.
Right, folks, the moment we've all been waiting for, the award ceremony. We are all winners for having attended RSS this year. And we will start with Best Student Paper Award. Here are our finalists. So we have Iterative Residual Policy for Goal-Conditioned Dynamic Manipulation of Deformable Objects. If the authors can please come to the stage. ACID, Action Conditional Implicit Visual Dynamics for Deformable Object Manipulation. Parameterized Differential Dynamic Programming. And AK, Attentive Kernel for Information Gathering. We're building up the suspense. All right, let's give them all a round of applause. And the winner of the Best Student Paper Award is... Nope. AK, Attentive Kernel for Information Gathering. And Chris, you want to stay with them for a photo? All right, thank you. Okay, let's draw this out. It's got to be like the Oscars. Okay. The finalists for the Best Systems Paper Award, which is awarded in memory of Seth Teller. Here we have Dexterity, Deformable Manipulation Can Be a Breeze. Viking, Vision-Based Kilometer Scale Navigation with Geographic Hints. Resilient multi-sensor exploration of multifarious environments with a team of aerial robots. And autonomously untangling long cables. And the winner is autonomously untangling long cables. Okay, thank you. And now, the nominees for Best Paper Award. All right, we have Iterative residual policy for goal-conditioned dynamic manipulation of deformable objects. Flowbot 3D, learning 3D articulation flow to manipulate articulated objects. You only demonstrate once category level manipulation from single visual demonstration. DIPCAN, 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 distilling privileged information for crowd-aware navigation. And multi-robot adversarial resilience using control barrier functions. And the winner of the Best Paper Award is Iterative Residual Policy for Goal-Conditioned Dynamic Manipulation of Deformable Objects. Congratulations to everyone, all the finalists.
All right, well, thank you everyone for all of your great papers. I have to say that there are fantastic papers, even that were not nominated. We have a very, well, the secret of a program committee is that it's a very noisy process, and there are fantastic papers throughout all of our papers. So I'd like to kind of move on to some acknowledgements. We have had a lot of people working hard on making this a successful conference. There was a lot of uncertainty about how this conference was going to play out due to COVID. Even within just a few months ago, we didn't know if we would have that banquet cruise. I am so glad we did, because that was like the perfect day. You know, it's the most beautiful day we could possibly have hoped for. But in any case, there were lots of people who were working on this very hard. First of all, from the kind of program side of things, the paper program, I want to thank all of our reviewers. Many of you are in this room. We had 370 reviewers, something like 700 reviews, and also hundreds of emergency reviews, which we could not have had this program without all of your emergency help. So a big, big thank you to all of those reviewers. Let's give them a big round of a hand. Round of a hand of applause. So these are just all of their names. You can't read any of them. It's okay. Oh, what? Okay, we switch to the screen. Okay. Yeah, you still can't read them. So. Another extremely important part of the review process were the area chairs. We had 25 area chairs for the conference. Area chairs are responsible for assigning reviews to papers, giving reports to papers, hopefully assigning some of their expertise to the whole review process. And without their expertise and sage advice, we wouldn't have the same quality of papers that we do and expect at an RSS conference. So let's give them a round of applause. And if you're an area chair, please stand up. No area chairs? We have a couple. I know Kostas is an area chair. There we go. There we go. There we go. Chris, yep. All right. All right, and we had a fantastic organizing committee. I'm going to name some of them one by one. So Xiaodong is here, and his work is yet to begin as he goes. Well, he did a bit of work putting up the program, and he will be inviting many of you to invite full journal versions of your papers. So we're going to be working on that. Florian Schruti was amazing at helping with the registrations. He was active throughout this whole thing, set up the feed loop site, and he is just an amazing guy. Florian, are you here? Stand up if you are. There you are. Let's give him a round of applause. Alberto Rodriguez is our sponsorship chair. Without him, we couldn't. He's the rainmaker, I guess. He really did an amazing job working with our sponsors and making sure that they had also good time themselves. We see many of them in this room, and he did a great job. Let's give him a round of applause. Luca Carlone, our publicity chair, could not make it, but he's been on Twitter and Facebook and LinkedIn and doing all sorts of social media blasts. He's been doing a great job too. Let's give him a round of applause. Yuka Zhu has been working on the website behind the scenes as well. He couldn't be here. He was supposed to be here, but he got COVID from CVPR, so we'll have to, hopefully he's watching on YouTube. He actually did a great job of alerting me to, I guess, some spammers on YouTube just a half hour ago. So Yuka, if you're watching, thank you very much. Let's give him a round of applause. I said that RSS is my favorite conference, but actually my favorite part of my favorite conference, when we're not having an amazing banquet, is the workshops. I love the workshops, and Sharon and Katya have been doing a great job. Let's give them a round of applause. Their job is not over either. We've had a great program for inclusion at RSS. We have Henny, who is still, Henny is here still, maybe? No? Oh. Back there, all the way back there, waving from seated. Let's give her a round of applause. And also Kalisha Bullard as well. Kalisha here? I haven't seen Kalisha. Okay. All right. And we had, I guess, really, really great feedback from RSS pioneers. You saw some of the photos if you're here during the break. Ali Harake and Nivi Kalavakanda did a fantastic job. Let's give them a round of applause. So here's just a couple of pictures from pioneers. I heard really great things. Mateo was saying he heard just as many positive remarks from pioneers as he did about the banquet, which is amazing because pioneers had about 40 people there. So a lot of great feedback there. I'd also like to thank our head honchos, so our general chair, Dylan Schell, and our foundation president, RSS Foundation president, Hadas Krazit, who are sitting here in the front row. If you guys want to stand up, let's give them a big round of applause for their sage advice. Mostly sitting back and telling us what to do from on high. My assistant, Abigail Barrett, helped many of you with your visa letters, so a round of applause for her, she's probably not watching, but it's okay. She'll watch the recording on YouTube, perhaps. And last but not least, we have had, well, in my opinion, a very successful RSS, and probably 99% of that goes to our, well, sorry, no, I need to, well, okay, the next two slides, you guys are 99% of what we owe the success of RSS to. First of all, the volunteers have done an amazing job. If there are any volunteers in the room, please stand up so we can all recognize you. You've helped with everything from registration, posters. You guys are the unsung heroes of RSS. Photos, AV, they have been indispensable to RSS. And the other folks who have been completely indispensable to RSS are our local arrangements chairs, Matej Chokarli, Yev Yeselivsky, and also doing double duty is actually Sharon Song. She has helped out tremendously with all of the workshops and also local arrangements. These guys they're the men and women who make this all possible. So let's give them a humongous round of applause. And I'm being pushed aside here.
Pushed aside, yes. So, hi everyone, I'm Daskas Gazit. You just saw my huge head there. So we don't have a slide, but we have the person right here. So, so for people who don't know, RSS tends to be very, very, very much program chair run. So local arrangements, oh my gosh. But also the amount of work that goes into creating this kind of conference and this program, from the review process to working with the ACs, working with local arrangements, deciding on what the program would look like, speakers, and all other things that happen are the PC's responsibility. And Chris has done a phenomenal job. And I would just like to, I know you clapped, but let's do that again. So thank you so much, Chris.
Thanks so much for the kind words, Hadas, and yeah, thank all of you for making this great as well. We couldn't have done it without you. Next up, we're going to talk a little bit about RSS 2023, and excuse me for 1 second while I grab my phone that's charging because I have an very official thing to say. Okay, as Hadas said, the program chair is one of the most important roles at RSS, deciding on many of the details of everything that goes on with RSS, and we do need to announce next year's program chair. I don't have a drum roll, but this would be an appropriate place to do it. So next, the drum roll for next year's program chair is Kostas Bekris of Rutgers University. So what's really important here at RSS is this a ceremony that we've kind of lost this over COVID, but this is something that's really essential to the success of RSS, which is the transfer of the ceremonial program chair Hawaiian shirt. So, Kostas, do you solemnly swear to sincerely carry out the duties of program chair and uphold the rigorous academic standards and sacred traditions of the RSS conference? Hold your hand up and say.
I do.
Do you swear to proudly wear the ceremonial program chair's Hawaiian shirt in honor of Nick Roy, which is essential to your duties as program chair?
Very essential, I do.
Do you swear, as required by your duties as program chair, to wear a Hawaiian or floral shirt each day for the following year until the next program chair is announced?
If you see me without one, you have to complain.
Yeah, you have to complain to Hadas if you don't see him with one. All right. Well, thank you, Kostas. And do you want to announce the local arrangements chairs?
Yeah, well, let me first say that, as Hadas said, amazing job. It raises the level of stress. You come here in the control room during the entire conference, and thank you again for all of the work and everyone that has organized RSS. So where are we going next year? Daeju, Korea, June 23, 28, approximate dates, 2023. And this is going to be the first RSS in Asia. And we're looking forward to a great experience, an amazing, convenient venue. It is an area that is a technology hub for Korea, experience, Korean culture, and with a strong industrial support. So local arrangement co-chairs, Han-Lim Choi from KAIST and Haewon Park. And there's going to be a big team in Korea supporting them. So a great round of applause as well for them and all the work that they will have to do.
Okay, so that's we're perfectly on time. This is great. So we have a little bit of time for the town hall, which is one of my a highlight for me because I get to hear from all of you. So Hadass and Dylan will be chairing this, but first I'm going to say a couple of words just from the review process, just to give you a little bit of context of. I mentioned a few questions at the beginning of the day. Many of you were nursing hangovers from the banquet, but I'll give you some statistics and also rehash some of those questions. So let me just give you some statistics. So we had 232 submissions. We had some desk rejects, and 74 were ultimately accepted. This is a 32% acceptance rate. And one thing that is one tidbit is that we did have about a 20% decrease in papers, both submitted and accepted from 2021. Whether this is a trend or not, I think we had similar sorts of trends in ICRA, but not shared with all conferences actually, which we'll talk about. So we have a very US heavy conference. If you look at the number of submissions, about 145 were from the US. If you break this down by continent, we do have a fair degree of European and Asian submissions, but definitely this is a North American centric conference, something to think about. Just in terms of the process, area chairs chose 3 reviews. We try to make sure that we have high quality reviews from our reviewers. We urge the area chairs to contact all of the reviewers if they don't have kind of sufficiently detailed responses to the papers. This works sometimes, and sometimes we have fantastic reviews, and sometimes we don't. I've had already some people complain about the quality of some of their reviews, and this is something that's very hard to control from my point of view. It really requires the reviewers to actually contribute that level of inspection and depth and feedback that we hope for. So even though the amount of word counts, the word counts in our reviews is relatively good, there's a huge standard deviation both above and below this. This year we chose to have an author rebuttal stage that was only seen by the area chair. This is because in previous years we found that having an author rebuttal tends to have sort of a contentious effect between the paper author and the reviewers, and the reviewers get entrenched, and so we thought that the area chair could use some of their kind of expertise and perspective to kind of put that rebuttal, it has sort of like a referee, kind of treat it from a third perspective. So we also have an area chair meeting, and discussion of your papers can sometimes be extremely extensive, and some of you who have been nominated for Best Paper Awards have had strong rejects as the first decision on your paper because of shoddy reviews. And so during the area chair meeting, we try to actually get the kernel of truth or scientific value out from your papers, and sometimes we have multiple readings. Even your area chairs work very hard to try to read your paper and see if it's actually, the reviews are actually valid. It's a very, very hard job, and the spread of our paper review scores is very small. So around 3 to 3.5, that's kind of on the low. 2.5 is high. We've got this range of 1 holds 90% of our papers. 1 score plus or minus 3 plus or minus 0.5. So it's a very, very hard job, and finding signal from the noise is very hard. Okay, so that's kind of the context from the review side of things, and we welcome questions and comments about the review process. There's also other topics that I raised in the morning. Many of you were kind of in bed trying to get sleep off a hangover or something, but in any case, we have some questions like how do we ensure high quality reviewing? How do we value systems research? Even though we do have Best Systems Paper Award, we still do not have that many papers on field robotics, on mechanisms, on engineering focused papers. Learning papers, as I've heard from many of you, seem to be dominating RSS, and if you look at if you go back here, learning is the first or second keyword in about 2/3 of our submitted papers and about 2/3 of our accepted papers. All the other topics are a little bit lower on that list, and some of them are almost not represented at all. So how do we kind of balance our focus on learning research versus other fields that are not really seen here at RSS? Another thing that we could talk about, I don't know if it's part of the scope of this discussion, but we have a lot of social change in the world nowadays, and is robotics, if this is the right venue to talk about how that's affecting our field? Where, if not, where should we talk about that? Well, I'll leave it up to you guys to find out. So, all right, well, so with that, I have nothing else, and we'll turn it over to Hadass and Dylan.
Thank you, Chris. So the purpose of this session is not really for us to talk at you. Chris made the joke that, he received instructions from upon high, but it's not very high. This is as high as it goes. The purpose of RSS is to have something where actually we can remain engaged with the needs of the community and we can be responsive to what people think. And so this session is intended to be a moment when we go to each of the microphones and have anyone in the audience who has something they'd like to say, and it can be anything from something you were happy about, it can be a response to any of these talking points, it can be something that you think was not handled particularly well, or should we say is an opportunity for improvement next time. Any of these things are things that now is the time to bring up, and if you're going to drag us over the coals, we can also respond in some cases if we think that that's appropriate. But really, this is more for us to listen than for us to go back and respond. So, David, do you want to take it away?
Sure, yeah. It's kind of just a minor thing to kick things off, but I noticed there wasn't an award for outstanding reviewers, and other conferences often do have such an award. I've heard from some grad students that it can sometimes be a motivating factor for them to put a little bit of extra effort, because if people see they got an outstanding reviewer award, then that's recognition that they want. And it also is just a nice way to recognize those people who put extra effort into their reviews. So, yeah.
Okay, thank you. Do you want to say something?
Yeah, I can honestly say I forgot. So I apologize for that. There's a lot of sort of things that we're focusing on besides that, but that's a really good thing to try to use. But I think there is also a broader discussion about how do we encourage high quality reviews, and that's one sort of recognition. I don't know if there's other ideas that people have.
All right, thank you everyone for an amazing conference. All right, a little closer. All right, there we go. That's significantly different. Thank you for taking these questions. All right, so on the last point, sustaining the health of our field. COVID, I had to help a lot of students find mental health care during COVID. First time depression. A student in our school killed himself. It's bad. I think it's really awesome that we use the legacy of Seth Teller to honor strong work in robotics and systems. I wonder if we should also be thinking about what we should do to make sure that nobody else takes their life by suicide. Should there be a Seth Teller award for mental health robotics, or a Seth Teller fellowship for exploring mental health in RSS? I think that's to start a long conversation. I know that's a very challenging topic for a lot of people who loved him, who knew him. I saw the grief of the students at MIT when we found out. And I don't mean to discredit any effort that anyone's doing to try to remember him, but I think it's an important topic that we should also be discussing. Thank you.
Hi, Jeffrey Herman from the University of Maryland. On the issue of reviewers, if determining a best reviewer is perhaps too much effort or too difficult, perhaps we can just acknowledge good reviewers with something like a gold star or something, giving them a special recognition. And the second point was, I was wondering if it'd be possible for this conference to provide a forum for researchers to bring and show off their actual robots. Thank you.
Thank you. Those are a couple of ideas I've never seen floated anywhere else. think there's the sorts of things we have to mull on a little bit. But I also know who asked those questions, so those might be people that I'll follow up with.
I think there are two things here, right? So there's what Matthew talked about, which is more systemic, I think, that needs to be, it's an interesting conversation to have at the board level, and this is more of a board level thing, I would say, as opposed to the other comment about displaying your robots, which I think that is something that might be worth kind of thinking about next year in terms of kind of, I don't know if, shipping and all that, but local arrangements and space and those considerations that can come into play, and some places it would be some places it will be easier to do, some places it would not be easier to do. So I think I really appreciate both ideas.
And I think there were a few instances where, I mean, there was a talk earlier this afternoon with, here's a system that I brought with me, come to my poster and you can see it. And the dexterity paper, which was playing the home field advantage, said come to the lab and you'll be able to see our robots actually working. I think that might have to do a little with this theme of trying to make sure we do take the robot systems part very seriously. So I think we should think about that carefully. Of course, in other conferences, one of the ways you wander around and you see physical robots is you see either exhibitors, which sometimes we've had at RSS, but it does depend on location, or competitions. So we've never, ever had any competitions affiliated with RSS. And we don't currently have a way for anyone to propose to do such a thing. So perhaps that's the thing we need to address there.
So we have a question at the top.
Hi, thank you for the great conference. So one of the points that I'm not exactly sure what the action item is, but this conference in particular, there were a lot of first-time conference goers, mostly because the pandemic sort of delayed the first conference of many new grad students. And this is sort of always true that we want to facilitate the first conference and make it easier for people to join in with the community. But I've seen a lot more discussion about concrete ways that we can help people self-organize around interest areas. And I think I would like to see if that's a thing that we would like to make more concrete in the future. But also, I think with the experience of having virtual conferences for a little while, I think it's important to think about ways to make that, or continue to make that accessible to people who aren't already present at the conference. And so I didn't get the sense that there was a lot of deliberate conversation in advance about the fact that there was a lot of new people, but this might be an opportunity to talk to a lot of people who had that experience at this conference and consider options for the future.
You're bringing great points, and I've observed this also with my students, how to explain how the experience of a conference in person is. And the other aspect that you brought up, which is, you now have the opportunity to meet some people that perhaps work in the same area, and you have the opportunity to interact with them. There are workshops that are happening around RSS, and I think, consider submitting applications next year together with people that perhaps you met here and you have common interests. These are great events where you can really focus and dive deeper into a specific sub-area and have very interactive discussions.
Two comments. First, with respect to bringing robots here, I don't know if anyone saw the Unitree robot dancing last night, but some people are bringing their robots. Second comment actually kind of dovetails on the last, although I was thinking about this previously. We had a format this time in which we wanted to have the speakers that were present and giving short talks, give a talk over a pre-recorded video, and I think we're all kind of grappling with the fact that we have this heritage now of Zoom conferences, and I think that it's great that we still are continuing to allow people to come remotely and attend and give their talks. I don't think that we should eliminate that, but I think we may consider adjusting the format for short talks And by that I mean, I think that having the person just talk over pre-recorded slides brings them a little bit closer to as if they were a remote member of our speaking cohort. And we might consider just having 2 podiums up or something like this, and one with the 5-minute talk, and it goes to the next one. And we've seen this model work previously where the mic gets cut off after 5 minutes. And that would help some of the cadence issues that the people who came to give a short talk actually had issues with maybe keeping track exactly with when their slides were advancing. That would give us all a different experience in that short talk. Just something to consider.
So Chris, actually the recorded talks predates COVID, right? So this happened, I think, since 2017. Definitely happened in MIT, but so we hear you. Costa's is going to take that into account. But the nice thing about it used to be, before we had the pre-recorded slides, there was a gong, which had its own charm. But people got gonged off the stage. But I think this kind of keeps a good cadence. So yeah.
It also simplifies. There is a motivation also to put everything on one laptop, and make sure that this is the local organizers' infrastructure. Everything will be working beforehand, and you're not going to have these issues. Oh, is my laptop working or not? There are things to balance, but I get your point, and I think I've seen also the dual podium work very well.
And I will say, although maybe people don't know this, there were a few teething issues, because I know there were 2 versions of videos that were submitted, and at least 2 speakers mentioned to me that the previous timing video had been played, and they were quite good at elongating some words and speeding up some others to kind of catch up. But that may have been why it was perhaps a little rougher in some cases. Not the speaker, but in fact we may have played the wrong version of the video in this case.
Yeah, that's somewhat my fault for choosing Google Forms for submitting your videos. It's really a nightmare. So Kostas, don't do that. We have a question up at the top. Or comment.
Hi. So I think that one of the things that makes RSS such a great community and conference is the quality of the reviewing experience. And one of the things I was pretty surprised pleasantly about on the first day of the conference was seeing just how many people are new to the community, how many people this is their first conference that they're attending. And one of the things I wanted to kind of put out there to maybe sustain this high quality is to see if there's interest in starting a reviewer mentor program, kind of similar to iClear's reviewer mentorship program that they started, I think this year for their conference. And I guess the question out to the folks on stage would be, like, is this something that you have any interest in supporting? And the question to all the folks who are sitting down is, if you are, perhaps a seasoned reviewer, would you be interested in being a mentor?
Let me just ask a separate question, since I'm blinded by the lights. Is that Brad?
Yes,
okay.
Yeah, Brad is.
All right. Good. I think it's an excellent idea. But I think we need someone perhaps who might lead that, and now I know who now we have a name. That was a bit flippant, but I do think it's something. I think it's one thing for us to say that we would like better reviewers, but we have to do something to improve the review process. And it is definitely, any of us who go through the process of teaching grad students know it's a skill that you learn, and a very valuable skill. And so I think something a little more structured like that would be quite valuable. I don't know too much about the iClear process, so I can't comment on that, but maybe someone else.
Yeah, and I was ready to say, any information that you have on what happened at iClear, please forward it to me so as to look over it. And anyone here in the audience that feels excited about reviewing next year, either on the junior side, and then they would perhaps appreciate some mentoring in the process and they have not done it before, or some of the more senior members of the community that would like to keep a very high standard for RSS, to be involved in this process, feel free to reach out to me.
You have a follow-up question? Oh, it was a thumbs up. Okay.
That was a thumbs up. I was also thinking that a number, especially of the graduate students who were out last night, probably got their IROS reviews while they were, having fun. And so if you are a senior graduate student or a PI who is also maybe not super pleased about some of the things that you saw, this is our chance to fix those problems here before they start.
Absolutely.
Hi. Yeah, as a grad student, I've come across the problem where if I want to write good papers, right? If I want to write a good paper, I just read good papers to get better at it, right? I read some great papers from RSS, from Micra, and when I think about writing great reviews, like there aren't any good sources for it. There's like openreview.net, but that's kind of a limited source and kind of like a limited field. Like how to write a great review for robotics, there aren't any sources that have great reviews that have been done before. So maybe a good suggestion would be not only just nominating a great reviewer as a prize, but also providing some samples of like great reviews that we received this conference. As an example, like say, you want to write a great review, here's a few examples. These were very informative because of this or that, and that's a great way to educate new reviewers, I think.
Okay. Thank you. I mean, we have to be a little careful about preserving anonymity, right? One of the things that we try to keep we do the best we can is to preserve the double-blind format for the conference, but I mean, it may be something we can do there, or perhaps there's a statute of limitations where we can show an earlier review or something. Yeah, or consent, yes.
Yeah, I just had a point following up on that because I was thinking similar things, especially for systems papers. I've been reviewing, oh, you can't hear. Can you hear me? Okay. Okay. Sorry, I just wanted to follow up because I was thinking very similar things for systems papers. I've been reviewing papers for many years, but I still find it very hard to review systems papers. My instinct is always to look for the technical novelty. And I know systems papers just have different evaluation criteria. So yeah, if there were at the least some guidelines of how should we review systems papers, but from talking to, I have a friend who works in learning science, and looking at examples is often one of the best ways to figure out how to do something. So yeah, maybe if we do release reviews, it would be good to have, if we do have some example good reviews, if we could have example good reviews for a, whatever non-systems paper is called, and then also a systems paper reviews.
I'll say that's quite humbling. If David Held is saying he has difficulty reviewing a systems paper, that shows you that's a hard task, right? So.
Hi, thank you for hosting the RSS. So I have a small suggestion about the presentation of the paper. So when I attended ICRA this year, so they're using a system called InfoVia. So basically it's a website that you can content the video, you can submit the posters, you can also submit the bullet points of the papers so that the people can also take a look at the website and get more information about the work. So I think RSS already have a very good website, but I'm just wondering if it's possible to contain more like multimedia material in the period, in the next year. So yeah, thank you.
Yeah, so I'll say a few things about that. So there is, of course, roboticsconference.org, which is the RSS conference, and then there's the roboticsproceedings.org, which is because all the proceedings are all available, right? And proceedings.org does not hold any multimedia content. It does have some additional information, but it doesn't have multimedia content. There is some multimedia content in supplementary papers, and there's some through the YouTube channels over the years, but they've never been fully integrated, which I recognize. We had a little bit of a discussion about this earlier at the board because there's some questions about then it's moving from a proceedings to something else. So we need to think about that a little more. But it's something on our radar that we need to do better. But I don't think we figured out exactly how we're going to do that. We can ask Hadass, wearing her other hat as ICRA program chair, if she has any thoughts on InfoVia, but maybe some thoughts, but maybe she won't share any of them. So.
I mean, yeah, InfoVia is another system as FeedLoop is, right? So the choice of which system you use has some of those properties. And this is something that typically we leave it to discussion. Well, COVID changed a bunch of things. So in 2020, when in March, we basically had to decide that we're not going to have RSS in Oregon. Then we had to find something quick. So feed loop came up in that. And then we've been using that, I think it was successful last year. I think it's successful today, this year, even though we're not quite, we're in person again. So the question of which kind of conference app to use is a good question. It comes with a lot of cost as well. And kind of one of the things that we try to do at RSS is to keep the cost as low as possible. I realize kind of, it could always be lower, but we still need to not, lose money. So there's a bunch of things. But InfoVia has some really good properties that we should take a look and see kind of what are the things that are worth keeping.
Okay, thank you so much.
It is not painless, let's put it that way.
So one suggestion coming back to the coming back to
can you the mic
to remove one suggestion coming back to the reviewing process and like what is systems paper, how can we review it and so on. It could be that we can integrate into the program a tutorial session. They did something similar in CVPR, but as a workshop for how to review papers. So we could have like something similar, like a tutorial on how to review and how to, for example, guidelines, what is a good systems paper, how to evaluate it. Something like this could be good, and it could like also give good guidance also for us to create better systems paper in general. Thank you.
Thank you.
Yeah, that's a great suggestion. And one of the issues with, I guess, so systems papers, we're talking a lot about them. We don't have a lot of systems papers submitted, but the reviews, I don't know if it's because of the people that we pick as reviewers, but the reviews tend to trash them, just to be frank. And so we can train, some of you to review, but if just by the luck of the draw, one of the reviewers tends to be, not trained, you'll just, also get similar types of feedback. But I think resources online, I like the ideas of resources online or examples if we can find people who consent to releasing their reviews. But it's a very good point that we may want to do more about the reviewer training process.
But it's more than that, right? So this has been it's robotics, science, and systems. And since I've been involved at RSS, the systems, it's always been a constant discussion. Why are we not getting more systems papers? Why are we not reviewing it better? And I think it's a point now that the really strong systems papers take a long time. The work takes a long time. So this is not something you can do in a few months. This is typically work of years that culminates in one paper. And I think the community that does that have been disillusioned by robotics, science, and systems because they were not reviewed well. And now we don't get those papers. I don't know, Chris, you would have better numbers than me, but, and I think one of the things is to reach out to your colleagues who are doing wonderful systems papers, systems work, and maybe other sides of your own research or your own labs that are doing systems work, and encourage them to submit. And on our side, it would be in making sure that the reviewers appreciate those kinds of papers, because those papers are, they are crucial for the field. They teach us a lot, but they're not a new algorithm necessarily. And that has been traditionally hard, and I think it's kind of like a chicken and egg. We're not getting those papers anymore. So now the ones we're getting are not, we don't feel like quite have all the reviews. So on one hand, I don't want to encourage people to submit their best work that will get trashed here. So hopefully that's not going to be the case. But it's a little bit of kind of and if you have ideas or specific people that we should kind of reach out to, any pilots we can try to doing, that is something that would be very much of interest to this community and also to kind of the leadership of this community, because those papers are amazing, right? So we'd like to see more of them.
I want to drop a kind of maybe strange suggestion just for getting brainstorming feedback. One thought is that we might want to take some sort of model like robotics and automation letters, in which we partner with a journal that focuses on more engineering heavy work, and say, well, you can submit your work to that journal, because these are a lot of times engineering disciplines that value that, like the journal model of publication, and then we could invite them to present their work at RSS. So we could have main RSS as well as RSS papers from Journal X, which are also presented at the same conference, so we at least get exposure to those folks. They get exposure to us, and maybe that's one artificial way of trying to make this a little bit more, get a little bit more of these underrepresented fields represented.
And I'd say just one thing, which is that if you haven't read Chris's open letter to the community, he put a lot of thought into it. It's a very well argued discussion of the status quo, and it shows you a program chair who thought really hard about this. And so maybe we didn't get as many systems papers as we would have liked.
And failed.
But I assure you, we did better than we would have if we hadn't had Chris, who was looking out for those papers. So it's a known hard issue. But if you are someone who has some thoughts on this and you haven't read the letter, you should, I think. Lorenzo?
Yeah, so partially related comment. So I think that one problem in general with the review process, not only for RSS, not specifically for RSS, but for our community, is that the time is becoming so long that you need so many months to get a review for the conference, and then if you want to submit the extended version to a journal, it takes forever, and in particular for a student for whom the time is short by nature, it's a problem. And as you guys were saying, if you're writing a systems paper, then it takes 2 years to complete the job, and then you need to wait 6 months for having the reply from the conference, and maybe it's negative, and blah, blah, blah. So I was wondering whether we could think of, in particular for RSS, for which the quality of the paper is typically quite high, maybe of some different model, maybe, I don't know, some direct journal publications after acceptance or something like this to encourage and to help speeding up a little bit the publication procedure.
Well, so maybe this is an example of being raked over the coals. So there's several people in this room who are waiting for reviews still for the special issue from RSS 2021, and I'm aware of that. And I'll say that there are unfortunately large delays in the journal process, but it's often not the reviewers, and it's actually often not the editorial people on our side who are incurring those delays. And I think evidence of that is when you look at the review timeline for RSS compared to, for example, IROS, which was brought up. It's pretty rapid. I think actually we're not the bad actors in this situation.
No, of course.
But I don't know, it's also a known issue in several of the journals. We can name names of journals that we know have a reputation. Let's not. But there's not that much I think we can do because after all, we're guest editors, right? So maybe what we need to do is perhaps think about what we can facilitate. So for example, when we have mature versions, maybe we could somehow associate them with the robotics proceedings, things more quickly, things that we have control over, I think. I don't know if anyone else has.
Yeah, another thought about the kind of long runway for these systems papers, the development process is very long. Perhaps there's some other mode of publicizing like intermediate work that is work in progress that can be somehow counted, and you have a presentation and you talk about your work in progress. I'm not sure what that would look like and what a half-done system, how that adds value to the conference, but it's a possibility. It's a possible mode that maybe Kostas and I can think about.
Thank you.
Thanks, Chris. I think I was going to say something very much on those same lines. So we've been talking a lot about like how you review systems papers, and I think another side of it is the question of like what does a good system paper look like and how do you write it. So I wanted to share an experience I had not with an RSS paper but another conference. I got a paper I reviewed a little while ago, and I think it was objectively a very poorly written paper, but an amazing system, which only became evident after looking at the very closely and seeing the like multimedia. And I think a big fact of this process is either people don't know how to write them, or it's a very fragmented group of people a lot of undergrads, and either we don't have consensus on what this paper needs to look like, or they have no clue how to write it. And we need to build up some framework here, and I don't know what it looks like.
I think we have even a definition issue, right, of what is a systems paper in the first place. We have referred, as examples, we refer to mechanisms, but it could be a pipeline, a software pipeline that puts together existing algorithms that does something new in terms of capability. So perhaps papers should self-identify as systems papers, yeah, and then have the guidance as well from our side. But yeah, it is a task, it seems, that we need to discuss about.
Rob?
Yeah, I think I wanted to suggest exactly what Kostas had just mentioned. So first of all, so David, I think David suggested early on that there were, we identify specific criteria against which systems papers would be evaluated. Authors could self-identify as systems papers to which those criteria would be applied. I don't know if that's a good idea or not, but just putting it out there.
Okay, so I think we've got a question up there.
Yeah, so I had a couple of things I wanted to say. Firstly, I wanted to say I really appreciate the removal of a page limit. I think that's very helpful because it's, sometimes it's very hard to squeeze into exactly the page limit, but having just an extra paragraph makes things much easier.
Are you speaking as an author or as a reviewer, right?
Both, actually. I don't mind reading a slightly longer paper if it means it can be a little more lucid about what's happening. Secondly, I wanted to voice my support for more openness in reviews. I know there's a trade-off between anonymity and openness that's hard to manage. But the last thing that I wanted to say, and this is more of my suggestion, is I wanted to suggest thinking about adding a statement for authors about the broader impacts of their work and the ethical implications of their work. Obviously, everybody thinks that their work is going to make the world better in some way, but the things that we are doing are going to have extremely far-reaching impacts, and making it explicit that this is something that should be considered, at least at some level, both by the authors and the reviewers, I think is something that's worthwhile. Even though everybody's going to say, this is going to make things better, I think going through that motion is still worthwhile.
So just to be clear, you're saying you think that would be something for the authors to provide in a paper, not a review criterion?
I think that should be something perhaps either as a brief note at the beginning or end of the paper. Something like a cover letter, perhaps, would be another option, and not a enormously weighted review criteria, but perhaps should be mentioned in reviews.
Okay. Henny?
Thank you so much to all of you for putting on such an exceptional conference and everybody who was involved. I have seen a little bit of how the sausage is made, and I know that everyone puts a ton of time and care into the conference. So we really appreciate it. I wanted to talk about one thing that I think RSS does really well, and I'd love to see continue, and one thing that I think we could consider for next year. I love that RSS is single track. And I know a lot of conferences are under a lot of pressure to add more papers, especially as the number of submissions increases and we want to be inclusive. And so I would just put in my vote for continuing the single track method structure because I think it's really valuable. I also...
Yes.
Great. Solved for next year. I also really love the fact that we have short talks and then a chance to dive deeper in poster sessions. I found it a little hard to hear in the poster session. I know that space is always constrained and it's so hard to find places to put all these people. But I would love to see a situation next year, especially, I mean, I've been to Expo, it's quite large, where we can have maybe more space or maybe soundproofing between the posters to make it just a little bit easier to have those conversations.
That's a good point. I'm not sure. She's got someone she's carrying, so we're going to let her go first.
Okay. Sorry. Thanks everybody, by the way, for tolerating baby noises in the back of the room. Oh, thank you to everybody for tolerating baby noises in the back of the room. I just wanted to add to the systems paper discussion. So I was one of the people behind making the award for Seth Teller with Matt Walter and Nick and John Leonard. And we've been having this discussion about what is a system paper for a long, long time. One of the goals we had in making the award was that we didn't really know. We thought about trying to write down what the good system paper is then, and we didn't really know. So we decided, I was sort of thinking, we're going to give some awards out, and now we have a corpus, right, of really good systems papers, award-winning papers at RSS. So for people asking, like, what makes a good systems paper, there's like an exemplar-based answer now that I encourage you all to check out. Thanks.
So the answer is data-driven, is what you're saying?
Of course.
Just sort of briefly following up on the question of systems papers, I know that a number of other conferences have developed alternate tracks to encourage papers that don't fit the traditional paradigm. So thinking somewhat of Alt-HRI and Alt-Chi, which allow non-standard tracks, as well as there's a design conference that allows works in progress submissions as a separate track. I'm not so much of a systems person myself, but I wonder if adding a track explicitly for works in progress or something like that would lower the sort of long-term risk for systems projects to be submitted, and if that's something we could explicitly use a model from other conferences to follow.
So one thing is, I will say, I'm going to echo what was said. They're really excellent workshops, and that is at least currently the venue for, I think, works in progress. There have been discussions about how much input the program chair should have over choices of workshops, or what sorts of things are selected for in the workshop selections. And so I think that probably varies from year to year, is I guess all I can say. Yeah, but I understand you're talking about a separate track in the main conference.
This is sort of now for something completely different point to raise, but it's, I don't know, quite close to my heart now and probably to other people's, is sustainability in the environment. Obviously, conference is an amazing place, like all these people coming together and sharing ideas, and that's kind of requires a lot of travel, and there will be a huge carbon footprint of that, and I'm not saying that's a bad thing, but I think it's important to consider things we can do while we're here to kind of mitigate that, and it was good to see things here like, I don't know, recyclable things next door, but also like the participation of virtual participants as well is, I think, something that's very good for that aspect, to allow people that maybe don't want to travel or can't travel to the conference for various reasons. And I kind of hope that in future, even when COVID is kind of a distant memory, hopefully, that's still an option for some people to attend a conference virtually and kind of get as much out of it as possible if they can't travel for whatever reason.
So I have a perspective on that from multiple conferences, and I think as much as I personally really do not enjoy virtual conferences as an attendee, I think it opened up access in a really amazing way. And I think all conferences will, hopefully, any conference that I have anything to do with will have a virtual option. So people would be able to participate somehow. Now, different conferences have different, just due to sizes, what you can do. There are some things that work pretty well, some things, I mean, poster sessions are super hard to do as remote. But yeah, that's a conversation that needs to keep on, I mean, we're going to keep innovating in that space for people who can't or don't want to travel but still want to be involved. I think, yeah. I think that if there's a silver lining in COVID, that's it. The fact that now people can access these ideas much more easily from home. I don't know.
Hi there. Yeah, thanks for a great conference. So I think one point I want to mention is around submitting code. So whether, what's the story with anonymity? For example, submitting a GitHub link or somewhere else, like will the code be looked at, and how anonymous is anonymous? And I think from the advice we got, it seemed like a gray area where there's maybe some mixed up incentives as to what exactly is preferred.
So I think just getting clear on the guidelines there would help, especially for systems papers, where maybe some of the value is in seeing the usage, the workflows, and so on.
Well, I think the Coral community is supporting something like this, and they encourage it, and I think there are ways to do it that are anonymous. You have to put some more effort. You have to not, perhaps giving an additional deadline of a few days for something like this may allow people to spend the time to make sure that there is anonymity, so it's like a repository that somehow it does not reveal. But I've seen it working elsewhere.
I also seen the opposite, right? So paper gets accepted, and then there's a reproducibility, like HSCC has that, right? The reproducibility badge that, there's code, someone can run it, and so on. But yeah, it's a good point, right? We definitely want to encourage that.
Do you want to go first?
Sure. So I already talked to Chris about this, but I wanted to say it publicly, which is something I would really like to see at RSS, is the addition of an accessibility chair. So this is something that the Chi community and SIG-Chi has been working to try and get added to all ACM conferences. And it can be someone who, from the very earliest days of the conference, is thinking about things like, will people be able to hear at the poster session? How are we going to get ASL translation? What is the physical accessibility of the venue? So this is something that I really feel strongly we should be doing in the robotics community, especially as we think about accessibility and assistive technology as major applications of our work. We also should be getting more disabled people in the room and actually working on these technologies. And I think making sure our conferences are accessible is a really easy, well, maybe not easy, but is a really important step in doing that.
100% agree with you, 100%. And we were just talking about that right before the session in terms of, I think for me, one of the goals for this coming year is to try to codify some of these things such that, we'll never, we're not, I want to make the process, I want to have guidelines for these conferences in terms of kind of what are the main things of accessibility that you have to deal with, that you have to ensure exist, and also who are the experts to go and ask their opinion about what are the things that actually are needed, because I'm not an expert in that. But just long-winded, you're right, we're going to do it.
I will add, I run trainings for accessibility chairs. So
say again?
I run trainings for accessibility chairs. So I'm happy to share all of my resources as well.
Yes, please.
I'd like to share a rather unorthodox idea. So that kind of aims to tackle both the problem of not having enough systems papers, but also sort of tackles the positivity bias we have in academia that we only publish like positive results. So one way that we could possibly incentivize the publication of systems papers is to consider hosting a workshop of great ideas that didn't work, right? From our experience and in our lab building the Trina system, for every great idea that we have like 4 systems that don't work until we get something that works, right? And in systems papers, usually you just keep working until it works. But if you had the chance to, okay, so we had this great design, we tried it, it didn't work. As long as you validate it properly, maybe presenting it in a workshop is useful. So you keep people from doing rework in the community just because they never left the lab. It's a weird idea, but.
Yeah, we had in Rome, there was a negative results workshop that I believe, Dylan, you organized, right? Yeah. So it was awesome. It was awesome. Yeah, so a workshop like that, it's a really lot of fun.
And I think we had a paper in this conference that had in the title negative results by Matthew Comolay's group. And this comes back to this community which is reviewing papers and submitting papers. I would definitely encourage people that come with strong statements that are negative and say don't try this. And then as reviewers you have to be open to this idea as well.
Hello. I wanted to echo the previous comment about broader impact statements and kind of forcing roboticists to think a little bit more critically about what they're actually building, both from a science and systems perspective. And I was wondering whether this kind of falls into that underrepresented areas that we would perhaps like to see more at RSS. There's a growing body of work, growing body of venues like fact, fairness, accountability, and transparency that do a lot of really interesting work about how our systems might be applied to the real world. And I was wondering whether you have any thoughts about like how we can better invite that into our venue here as well.
So I'm not sure if I got everything you said, but I think, for example, picking up, the one thing that has been discussed once was to do something a little like AAAI does, or AAAI does, where they invite some of the best papers from different communities. In fact, some years ago, some of the very best RSS papers were presented at AAAI for several years. So it may be that people who think hard about the transparency of a particular system that they're building, maybe if you're saying that there's a strong community around that, perhaps we should consider having a track where we invite the best of the rest, I think it's sometimes called. And that could be one subset that we consider. Yeah, I think it's a good idea. I don't quite know how to move forward with that other than maybe to say perhaps, to everyone, which is when I was program chair, I did get emails from people saying, I think you should do this. And they were often very well thought out, very well argued emails. And so I would encourage you to do the same for the following year if you have some thoughts about something you think, some particular thing which is as precise as you've said, which we could try to incorporate in the program in some way. Micah, right? I think, are we out how are we doing for time?
We've got 14.
Okay, here, go ahead.
So I'm here to continue beating the systems paper problem to death. Building on Ruben's comment and maybe a bit of a tangent. So Ruben's comment a few minutes ago regarding different tracks got me thinking and maybe on a bit of a tangent. So I think in the past we talked about things like adding videos as a way to highlight systems papers, and I think maybe that's a hard thing. I think one thing maybe we could do is try to recognize systems themselves, in addition to systems papers, as a more focused and maybe lower bar, because I think there's a lot of good systems out there, but maybe not always the people to write about them. And if we have a way to either recognize papers that weren't accepted or to accept submissions or nominations of excellent systems, then we can start highlighting and building that community here again.
I'm not sure about this because in the end, you have to be able to communicate the benefit of the system in some form that can be easily passed along. I think we have supplementary material, right? We have videos that I think do influence the review process, where perhaps you can communicate the power of a system through a demonstration. But the way that perhaps I understood your suggestion, it may not be correct, is that perhaps we should have a lower bar on the manuscript side of the submission. I think we should have a requirement that the message and the benefit of that system is adequately supported by the manuscript.
I think we can do a bit of both, and I think I'm coming from a mindset of we need to find ways to include the people who are building good systems, in addition to finding ways to enable them to write good papers.
I think there's one at the top.
Hi there. I just wanted to give a big shout out to the Inclusion at RSS program, and a huge thank you to Henny and Kalisha who organized it. I think one thing that would be awesome for next year for the future Inclusion Fellows would be if there were like a poster session where all the Inclusion Fellows can present something. That's all.
Cool.
I'm just contributing a idea. I don't know if that works or not. So maybe we can do something like open source system. You kind of like have some like a website describing how to replicate your system on the other locations or other labs so that people can repeat your results in a short time or something like that. And that kind of paper maybe can be encouraged more to be published in conference like this or like a journal, something like that. So yeah, just the idea.
So I will say you have the power to do that, because when you review a paper, and I've seen many reviews that do this, they say one of the really great things about this paper is how replicable it is, because I went to the website and I could download the code and I could run the code, and this really works. So we could recognize it in some way, impose a constraint, but in some sense that's already a value that if you think is important, we can all recognize, right?
Yeah, so I was just saying, like, maybe you can promoting some kind of ideas like this, because right now I don't feel like something like this really being like recognized or promoted. More like it's more like a personal thing, so like just individually doing such a thing. So yeah, that's the idea. Yeah.
And reproducibility of results, I think robotics is a very big issue that is discussed a lot, and it is harder than some of our neighboring fields like computer vision and machine learning, because some of the code is linked to a physical robot that may be very specific to the lab and is not easily transferable. But definitely, if there is a component that can be easily reproduced, we should encourage this. And again, as reviewers, encourage of using that code and trying it out.
Is there a question? No? Okay. Going once. Going twice. Okay, I think that's it.
So usually our tradition would hold that you close the RSS conference with a gong, but unfortunately a few years ago the gong was lost to the sands of time. So I'm just going to say it, gong. Enjoy the workshops tomorrow. Have a safe trip back. And yeah, great to see everyone here.